what's also ahead in more futuristic scenarios of using this green hydrogen to do some downstreaming to other energy carriers obtained from this green hydrogen, overcoming some restrictions of hydrogen. So today we are making also use of some colleagues that are with us this week in the Canary Islands. We have a group of experts of the International Energy Agency that they have been meeting here at Pozo Izquierdo for the last two days. They were holding we hosted a meeting on Monday and Tuesday, and we have, for us, has been a real honor, and well, we will have also participation of experts. Regarding the Canary Islands Institute of Technology, we are a company belonging 100% to the regional government of the Canary Islands, and we are focusing our activity on technical solutions for maximizing renewable energy penetration in island systems, basically small and weak electrical island systems that are being exposed to variability, intermittence of renewable energies, and in scenarios of growing renewable energy penetration, we have big challenges, okay? We are addressing these challenges with a strategy that includes, among other, energy storage, and this is where hydrogen is important for us, to be able to, from the demand, do some grid balancing of the electrical island grid using the electrolyzers as part of the demand-side management strategies, electrolyzers that will allow us to produce green hydrogen from renewables for energy storage, but also use this hydrogen, as I mentioned before, also as an energy carrier for applying renewables to transport, not only road transport, but also marine transport and aviation transport also in maybe a longer term horizon, okay? So not to lose more time, I think that we should just go ahead with our first speaker. The first speaker is Pedro Mendes. Pedro is from Portugal, but he's currently at the European Commission. He's policy officer of the Directorate General for R&D of the European Commission. He's representing the European Commission at the International Energy Agency groups working on hydrogen technologies, okay? So Pedro, if you please could begin your presentation, the floor is yours, okay?
Yes, thank you very much, Salvador, first of all, and thank you. And it's a great honor to be here present in the Instituto Tecnológico de Canarias for this launching event of the project, and also for the very kind hosting of our IEA TCP meeting on hydrogen. So, as presented, my name is Pedro Mendes. I work at the European Commission. And I work in the Directorate General for Research and Innovation Policy. So we focus on deciding and allocating the budget under the European Union Framework Program for Research and Innovation, or as in Europe, to fund hydrogen projects around the European territory. Today I'll talk to you about the Clean Hydrogen Joint Undertaking, or also called Clean Hydrogen Partnership, which is a public-private partnership that has on the public side the European Commission. The European Commission is represented both on the research side and also on the mobility and on the energy policy side, and we have the private members of the partnership, which are Hydrogen Europe and Hydrogen Europe Research. These are two industry associations focused in Brussels and based in Brussels, and together they compete more than 500 different members. This partnership was established in November 2021 and followed on the work of the two previous partnerships that you may have heard about, namely the fuel cells and hydrogen partnerships. The budget for the whole period of 7 years is of 1 million euros, and this budget has been topped up in May of last year with 200 million euros extra to fund projects like the so-called hydrogen valleys, or so-called hydrogen hubs in countries like the US. These hydrogen valleys, I'll present them further on. I know that there is interest in the audience and probably here in the Canary Islands to have these hydrogen valleys developed in the region. And we have already some projects around Europe where we focused in particular on the whole supply chain. The priorities of the Clean Hydrogen Partnership currently are hydrogen production. In the past, we have funded a lot of transport projects, but nowadays, this Clean Hydrogen Partnership is focused specifically on the production of green hydrogen, so hydrogen from electrolysis, as we have here in the institute. Until now, the Clean Hydrogen Joint Undertaking has funded almost 1.4 billion euros of projects. Most of them have been in transport. As mentioned in the previous iterations of the partnership, the focus was more on transport than it was on production, which is the focus now. We have funded also a lot of end uses on clean heat and power. Storage, as you can see, only has 6% of the funding, which is what you consider being the weakest link nowadays in the European Union, because we are producing a lot of hydrogen, but we don't really have the capacity yet to store it. And this is something that we hope in future calls we will be improving. Of course, not all projects are still included here because we are currently under grant agreement preparation regarding projects from this year's call and last year's call. The call from this year expired in April, and the call of proposals for next year will be likely published in the beginning of next year, as it was for this year. The priorities that we have, as mentioned, the main priority is really the production. We talk about electrolysis, but we can also talk about other routes for production of green hydrogen. So this is very important. We talk about green hydrogen, clean hydrogen, not low carbon hydrogen, not blue hydrogen, which is not excluded from funding from the European Commission, but not at the research side. And then we have been including a lot of other different priorities, namely, as mentioned, on transport applications, where we focus more on heavy-duty transport, so buses and trucks, not necessarily in cars. In fact, specifically not in cars. And we focus a lot also on stationary applications. This year, in the call for proposals, we had a total budget of almost 200 million euros. The 5 flagships that were mentioned focus a lot on local pipeline networks, on underground storage. We fund hydrogen valleys of different dimensions, some more ambitious, large-scale valley to produce thousands of tons of hydrogen, and some others at a smaller scale. And in general, we fund the biggest share of work for skills, because we have currently a workforce that's not ready to engage and to work in the hydrogen industry as much as in other energy industries. So it's important for us to know, and being this the European year of skills in the European Union, to know that we have a big base of development of competences. We also focus on regulations, codes, and standards in the joint undertaking, because it's the intention of the European Commission to both produce hydrogen and to import hydrogen, and so it's important to standardize. The results of the call from last year, we have received 132 proposals. More than half of them have been qualified above threshold. And it's worth noting that the topic on electrolysis production is the one that received more proposals, which shows the interest of the community of the industry in developing and accelerating the production of hydrogen. And also for the hydrogen valley proposals, we have received, unfortunately, most of the proposals have not met the threshold, even though we will still be funding five hydrogen valleys. This is a situation we know that there has been some uncertainty around Europe on where exactly constitutes a hydrogen valley, on the regulatory framework. And this is something that we've been working together with the industry, with you, with the community. I'll be talking about a roadmap later on in the presentation. The Clean Hydrogen Partnership also focuses on international cooperation. It is the role of the partnership to support the European Commission in its relations with other stakeholders and with the rest of the community around the world. We talk about, for example, the partnership with the African Union on hydrogen. We talk about mission innovation, particularly the clean hydrogen mission, where we at the IATCP also focus with, because when we talk about this green transition, creating the hydrogen economy, we talk about a global mission, not only an EU mission, and it's important that we have it clear in mind, both from our side and from of course everybody's side. And then we also talk about cooperation with the Mediterranean. It's a very important region for the European Union, given the abundance of energy and water resources. And so it's very important that we have a development of further cooperation, further projects in the region. Now, focusing on hydrogen valleys, the Clean Hydrogen Joint Undertaking has been having a PDA program, a Project Development Assistance Initiative, where it helps regions, it helps potential developers in understanding better and developing their projects to be able to apply to the Clean Hydrogen Partnership calls to develop a hydrogen valley. This has been the expressed intention of the President Ursula von der Leyen, and right now we have a Hydrogen Valleys Partnership that features most regions in the European Union. Again, also as mentioned, last year under the Repower EU plan to diversify and to reduce the dependence on fossil fuels and energy from Russia, we have talked about doubling this number of hydrogen valleys in the European Union, which is a main flagship right now of the European Union funding to hydrogen. The Clean Hydrogen Partnership until now has funded three projects in the past, since 2015. And then after the call for proposals from last year, 9 more hydrogen valleys are being funded. Here we can see the location. So it's our intention to have them spread out across the territory of the Union. We have the number one, the Green Highland, here in Spain, in the Baleares. Right now, under the annual work program for 2023, as mentioned before, we have 5 proposals above threshold. These 200 million euros of extra money that we have to fund these hydrogen valleys are going to be in place until next year. All of this, the way the money is distributed, the way the money is used, is part of the call for proposals of the joint undertaking, and they are available to be consulted, just like me and my colleagues in case of any questions. We are currently elaborating a roadmap, because we have this objective of doubling its number in 2025. We have identified already 55 hydrogen valleys in the EU. However, most of these hydrogen valleys are still in a stage of still talking about the development, right? So as we often say, they are still a PowerPoint presentation. And so it's our intention to accelerate and to help developers with it. We have identified the need for the publication of Hydrogen Valleys roadmap. We have consulted the industry. We have consulted every stakeholder that had an opinion. We had a call for evidence open until the end of the summer, and we got more than 120 different responses. These have been the main barriers identified in that call for evidence, which we are currently working on. The Hydrogen Valleys roadmap will be published by the end of this year or beginning of next year, so we should expect it in the coming months. And main barriers identified have been the cost effectiveness of the production, which is where other instruments like the European Hydrogen Bank is coming into place as well, to try to bridge this gap between production of more expensive hydrogen and the costs necessary to do it. Of course, we also know that the regulatory framework has been unclear in the European territory, which is why we published these two hydrogen delegated acts in March. And the hydrogen storage and transportation have been, as mentioned before as well, the weakest link. Thank you very much. I would like to extend also my invitation to you to be in Brussels in November for the European Hydrogen Week. It takes place from the 20th to 24th of November, and we'll have a lot of stakeholders present. We'll have a business-to-business forum, as well as a high policy conference where you can give your input to the community, to us in the European Commission, and the Clean Hydrogen Partnership, and it will be a success, hopefully. Thank you.
Okay, so thank you. And also that you have mentioned the importance of other aspects, not only technical, but also social, the need for capacity building, for training, and also for international cooperation. No? And then the hydrogen valleys. You are promoting this very comprehensive strategy based on hydrogen valleys, but what, at least I wish we could see more our island regions participating in these hydrogen valleys for reasons we have been discussing, no? That the European islands are excellent living labs for developing all these initiatives of integration of renewable energies and hydrogen technologies. Pedro, thank you very much. We will leave the questions for the end of the session. We have some delays, and thank you for being for adjusting to the time, okay? Thank you, Pedro. Well, our next speaker, Santiago Gonzalez. Santiago, he will brief us on the regulatory framework and measures developed for promoting green hydrogen and biofuels in Spain. Santiago Gonzalez, he's the head of the Green Hydrogen Department at the Institute of Diversification and Savings of Energy, it's IDAE, the Spanish reference for promoting renewables and energy efficiency. So please, Santiago, the floor is yours.
Hello, buenos días. Good morning to everyone. Thank you very much for this introduction, and thank you very much to the organizers for the invitation, the kind invitation to IDAE to participate in this conference. I excuse my directors, Joan and Victor, who couldn't make it, and that's why I'm today here. I would like to start with a short introduction to IDAE. As this is an international conference, I presume not all of you know exactly what the role and activities of IDAE are. IDAE has a long track record of nearly 40 years in the energy domain. Is the Spanish branch body which depends on the Secretariat of Energy from the Ministry of Ecological Transition and Demographic Challenge. And it's got 6 different directorates, and in particular for renewable energies and directorate and electricity market integration is where my department was created just a few months ago. With regard to the functions that IDAE is performing as of today, we can see here that one of the main areas is to provide technical assistance and support to the ministry in the different areas of energy policies. We also conduct support schemes, design and approve these schemes, and we launched the different calls for providing the funds. I must say that in the last few years, this activity has been, in the case of hydrogen, even more than 100% of the total activities devoted on a daily basis. Also, we are channeling some funds to the investments and participation in projects. For instance, one of the projects, which is the one in Mallorca, in Lloseta, which is a pioneer project for hydrogen, renewable hydrogen, we participate with an 8% as a shareholder in the company which is running this project. There are other examples. We have a long track record of participation in different investments. And as well, communication and dissemination is one of the must areas in which we have to project our activities, and we need to go farther in order to reach out all the different stakeholders and citizens and other policymakers, and coordination with the different other regions all over Spain. So once this introduction is made, I would like to enter into what the context we have today in renewable hydrogen, in renewable energies as a whole. As you know, directive from 2009 and subsequently directive from 2018 on renewable energies, this last one was Directive Energy Renewables 2, established a regulatory framework for the promotion of the use of energy from renewable sources, setting targets for the share of renewable energies to be achieved in energy consumption and in the transport sector. The revision of this recently agreed directive, RED 3, sets out more ambitious targets, including inter alia the following ones, which you can see here in the right-hand column. Increase the share of renewable energy in the total energy consumption to 42.5%, with an additional indicative supplement of 2.5. That means to reaching 45% in 2030 in all energy consumptions, final energy consumptions. A secondary binding reduction target of 14.5% of greenhouse gases intensity in the transport sector through the use of renewable energy. Alternatively, a binding share of at least 29% of renewable energy in the final energy consumption in the transport sector, compared to the previous 14%, is to be followed by the different approaches of the member states. In addition, a 5.5% binding combined sub-goal for advanced biofuels and renewable fuels of non-biological origin. This is mainly renewable hydrogen and synthetic hydrogen fuels. All of them should be met by this year, 2030. I would like to mention that as well, biogas and biomethane can make a significant contribution to achieving these objectives, not only the renewable hydrogen. In this context, we have the REPowerEU, which, as you know, in May 2022, the European Commission presented this REPower plan in a response on the global energy market disturbances caused by the Russian invasion of Ukraine. This plan is committed to diversification, energy savings, and the acceleration of the development of clean energy in order to reduce the vulnerability of the European Union's external energy dependence. There is one element which was introduced in this REPower plan, which is this hydrogen accelerator, which involved to double the objective of previous written down in the strategy for hydrogen, which was 10 million hydrogen consumed in the European Union, and that meant that it was doubled by importing additional hydrogen produced in the neighboring countries around the European Union. In order to meet these goals, the European Commission proposed a number of measures in the short, mid, and long-term intensive industries where the hydrogen, grey hydrogen is substantially consumed, and to displace these fossil fuels by the use of green hydrogen. To boost these new measures, as well, the Commission put in place an element. It is named the Hydrogen Bank, but indeed it's not a bank. is a set of activities in order to create as a market maker of putting in cohesion the suppliers and the demand of renewable hydrogen all over Europe. This is one of the auctions that will be open this next month, 23rd of November, for instance, with a provision of 800 million euros. So these are a set of elements that are addressing the ambitious goals for hydrogen, which were enhanced by this very plan. But there are also other elements that are related with, for instance, biomethane and biogas in order to improve and facilitate the reduction of dependency and improve the security of supply for energy in the European Union. The long-term decarbonization strategy for 2050, this was a document that was approved by the Spanish government at national level and charts the way to achieving the climate neutrality target in 2050. In this regard, hydrogen, renewable hydrogen and biogas, we are sure that will play a very important role in order to achieve the targets of neutrality in this very year 2050. With those technologies and those solutions that are being tested today, but we think that will be ready for the years, especially for the period beyond 2030, and in particular will be massively deployed in 2050. The renewable hydrogen roadmap, Spanish renewable hydrogen roadmap, which was approved in October 2020, is a roadmap that is only focused on renewable hydrogen. This is a political decision not to promote and to focus on any other type of colors or hydrogens of other origin, which are related with carbon or fossil fuels. It is very focused on hard-to-abate sectors, in particular those industries that already consume gray hydrogen, and also the transport, means of transport, heavy transport, that renewable hydrogen is a promising solution and pays dividends, and it's more competitive in the long run compared to direct electrification or other alternatives. The gray hydrogen replacement is a goal, a particular goal, and it's very important to push the value chain of hydrogen in order to align the capacities, the knowledge, and the possibilities to enhance the economy, the Spanish economy, and have a reduction of dependency of fossil fuels, but as well a reduction or increase in the technology autonomy, the dependence of other technologies and other countries in this regard. These are a summary of the different targets. The main target was the 4 gigawatts of installed capacity in 2030, with a displacement of 25% of this grey hydrogen. And there is a number of different goals, 150 hydrogen refueling stations, a number of buses up and running at this year, in this year, 2030, and with the promise of mobilization of nearly 9 billion euros of investments in the production of renewable hydrogen in the total period until 2030. With regard to this roadmap, we have different segments of the roadmap. The regulatory tools that we're addressing, as you can see here, mostly have been implemented, in particular the administrative simplification, production and supply lines, dedicated lines. Public interest granted for isolated and injection hydrogen pipelines, it's also done. The system of guarantees of origin was, this scheme was approved by Royal Decree in May last year, which encompasses not only hydrogen, renewable hydrogen, and in particular for the sectoral tools, funding lines were foreseen. We are actively continuing working on that, and in this very moment I would like to mention, which it might be a bit of a spoiler to the end of the presentation, that just yesterday the Council gave the green light to the addendum of additional funds for in order to provide funds for renewable energies, but in particular for renewable hydrogen. Renewable hydrogen will have another 1,600 million euros in Spain to boost new developments and new projects in the pipeline. Mobility incentives for the purchase of vehicles and deployment of hydrogen refueling stations it was something that we incentivized through the Pioneer line of action, and sector integration and the adoption of hydrogen as a new element of the new national statistics in convergence with Eurostat provisions and work. It's also something that has been advanced. Together with other areas like related with training and skills and boosting R&D are elements that have been covered insofar as the implementation of this roadmap that encompass 60 measures. These advances in permitting, I would like to zoom in some of these. In terms of governance, the coordination at national and regional level has been enhanced. Amending of the law on hydrocarbons have included the permitting procedures for renewable gases pipelines, providing more legal certainty, the declaration of public interest for the injection lines into the natural gas grid, and the new provision implemented related with the isolated pipelines for renewable gases, in particular for renewable hydrogen and biomethane. Also has been reduced the requirements in terms of the impact assessment for permitting an electrolyzer installation. This is something that has been amended in the environmental impact assessment law. And as well, I would like to mention that the existence of temporary cancellation of the shares which are a large consumer of electricity in the case of electrolyzer. This is something that has been implemented for this year, this exemption of charges. Together with this, we have a very important piece of legislation which is now being decided and nearly on the verge of approval is the package on gas and hydrogen, which will need to be published and approved by the end of the year and transposed in the national legislation later on. This is something that I already explained, the system for guarantees of origin. So the next steps in terms of the hydrogen roadmap, we have the National Integrated Energy and Climate Plan, which will inform the update of the roadmap for the end of this year, beginning of the next one. The regulation, we will follow up on the sectoral regulation transposing gas and hydrogen package, and also transposing those different directives and regulations that form part of the Fit for 55. There are up and running several subgroups of consultation on these very items and topics led by the Ministry and by the Secretary of Energy advisory groups on hydrogen, which are continuously ongoing. Entering to the National Energy Plan, in order to achieve a harmonized way among the member states, this national plan was published in March 2021 for 2030, and now has been updated. It's been in consultation until beginning of last month, September, and has increased the number of measures that were covered in order to accommodate the elements that are related with the agreement reached on RED 3 and following the Repower EU plan, and etc. No? This draft encompasses 107 measures compared to the 78 previously, and these 46 are new or have been updated from the previous versions. These are the targets which have been increased in terms of reductions of energy of emissions, in terms of energy efficiency improvements, in terms of 81% of the renewables share in electricity, and 48% of renewable energies in all of the sectors. This is an indication of the sub-targets that are encompassing in the mobility sector, which, as you can see here, is a great improvement, even above the Fit for 55 package, and in particular for the percentage of renewable fuels of non-biological origin is multiplied per 3 in the target compared to the previous one in the roadmap. We have a new target which is to be inserted into this updated roadmap of renewable hydrogen, which nearly triples the target of 4 gigawatts of electrolyzers to 11 gigawatts. It's quite a challenge to have up and running such a figure, we know. And we have also other accompanying ambitious targets, which are related, this one on biogas, which is as well doubling the former from the roadmap, and others which are related with more areas, technology, cross-cutting technologies. The measures which are identified and are new are listed in here, and recipients targets of different sectors in transport, in industry, but also it might be in commercial or residential sectors. No? Dipping into the funding programs, component 9 was the component devoted to renewable hydrogen. This was divided into 4 main axes. The first of all was innovative value chain to improve the capacities, the knowledge, to really have research and development in place and collaboration between companies, SMEs, and as well centers of technology. This, we provided 250 million euros of funding in 4 different programs. And as well, we opened a second call of nearly 67 million euros for additional pilot projects and industrial research and demonstrations. We have the hydrogen valleys, which now we have notified a scheme which is now under the process of request for information from the Commission side to the Spanish authorities, which is supposed to have a new mechanism to provide funds for large projects which encompass production and consumption into the same area. This is something which we had it pending. And the third element, the third axis, is the pioneer projects. These are ecosystems of hydrogen which are starting from a small capacity to upscaling to larger capacities to demonstrate the feasibility and the viability of having an ecosystem based on hydrogen to really displace the fossil fuel and introduce hydrogen in brand new consumers, like for instance mobility and so on. IPCI is a very special tool, which, as you know, is in coordination with other member states. We notified the first 2 waves, which were addressing technology on the left-hand side and the decarbonization of the industry on the right-hand side. A number of projects were chosen by member states and then endorsed in a decision by DG Comp. And in the first wave, there were 4 projects, Spanish projects, and in the second wave, 7 projects with very ambitious targets and different elements. Finally, I would like to mention what I already said before, that yesterday the European Commission, the Council gave the green light and endorsed the new addenda, which encompassed nearly 3,200 million euros additionally to the existing ones from the program of recovery, and out of them 1.6 billion euros will be devoted for hydrogen. Also, there are some elements related with the value chain on manufacturing of key technologies for renewables capacities. In particular, electrolysis will also be eligible in this other tranche of monies, which is this 1,000 million euros to be taken into account. So I think I exceeded the time, or stick. Okay.
Thank you very much.
So.
I have some things to mention here in your presentation. Santiago, we will have the opportunity again, because we are not running out of time, but we should keep the schedule as planned. No? But there's sorry. Yeah, sorry. Okay. Yeah, the microphone was not open. Yeah, Santiago, I just want to ask you, because there's a very interesting and very practical approach of IDAE. I mean, when Santiago mentioned equity participation, he's not talking about earning money in the projects. We had experience, the first wind farms in the Canary Islands, some of them were participated by IDAE, but really what IDAE was looking, and is still looking for, is learning from suffering the process of promoting a project. And this knowledge usually translates into streamlining bureaucratic procedures. So I think it's a very interesting approach, being on the other side sometimes, I mean, suffering what the private promoters have to go through in order to promote these new sustainable projects. I don't know, Santiago, if you want to comment on that?
Yes, sure. Absolutely. I think it's an academy for us, I would say, because it's a sandbox approach in real life projects in which you can participate with other partners in the development from scratch of a project, from permitting to execution and then running, and having a first-hand approach and information on what are the problems, the real problems that are tackling these new solutions, this new business model, because in the end it's the business model which is behind the one we want to lever and to promote in other parts of Spain, and to learn from advancing in the specific locations that are very committed to deploy that.
Okay. Thanks, Santiago, and thank IDAE for all this sensitivity they always show towards the Spanish islands. We are lucky to have IDAE's director, Joan Grisart. He's from Mallorca, so I guess that also helps, no? And thank you for your presentation. Very nice.
Thank you.
Thank you, Santiago. Yes, so we were addressing very financial related issues from the information we received from the European Commission, from Pedro Mendes, and then from how Spain is in coordination with the European Commission strategies for financing projects through the policy that IDAE is promoting. And now we will go to more technical discussions. We will have with us, representing the Ministry of Defense, the Spanish Air Force, we have Captain Enrique Cabezas, and he will tell us, he will brief us on the role of e-fuels in military operation. Please, Captain Cabezas, the floor is yours. Yeah.
Thank you very much. Thank you everybody for coming today. First of all, I'm introducing myself a little bit. I'm Captain Enrique Cabezas. I'm aerospace engineer, and I'm posted here in Gando Air Base. I'm in charge of F-18 fighter aircraft fleet maintenance. And I was invited to speak about the role of e-fuels in military operations, so I decided to focus in the Air Force, as is what I know the most. I would like to speak about these points. First of all, the reasons to focus on e-fuels from the military point of view. What is the NATO's state of the art, as well the Spanish one, the Spanish Air Force, in the last slide. And I would like to speak a little bit about the SEPs, just for you to understand the importance to us, and the regulatory framework, both civilian and military as well. First of all, about the reasons, e-fuels they are as safe as conventional fuels, so they follow the same regulations. So it's important to know the first point. And they enable us the drop-in technology, so there is no extra cost. We can use them directly without mechanical modifications. Apart from that, they are the only short-term solutions to aviation, just to get the emissions reduction by 2050. Although, for the moment, the military operations are exempted, but we do not want to duplicate the systems, the pipelines, or the ships. And as well, they can be adapted to have even better properties than fossil fuels. So we can go beyond better attitudes, such as higher altitudes, for example. And last but not least is readiness. It's important that Spain don't lag behind the other countries from NATO, because NATO has the necessity to be able to interoperate between all of them. So Spain cannot lag behind the others. And the competence of approving all aircraft is from every country. About the NATO's state of the art, we have one organization inside, is the Science and Technology Organization. This is like kind of research and development department in NATO. And inside this organization, there exists a working group called the AVT, Applied Vehicle Technology, which is investigating this area. They have published the technical report 225, titled Military User's Guide for the Certification of Aviation Platforms on Synthetic Jet Fuels. And as it is written, it arises from the need of NATO countries of maintaining the Air Force operations in case of a possible scarcity of conventional fuels, supply cut, limited petroleum reserves, natural disasters, international conflicts, such as the Ukraine war just was mentioned before. And in this picture is shown the CEPS, the Central Europe Pipeline System. As you can see, Spain is not included, not even the Canaries, but helps to understand the problem. The problem basically is that we cannot duplicate all the pipelines, so we need them to be used for both synthetic and fossil fuels. And as you can see, we use ships just to put the fuel in the line. And those ships are, we bring our fuel here in the Canaries with the same ships. So we need them to be used for both of them. About the civilian regulatory framework in aviation, we have first of all the ASTM, American Society for Testing and Materials, the Delta 1655, which covers the Jet A and Jet A1. They are the most common fuels for civilian aviation. And on the other hand, we have the Delta 7566. This standard covers the fuels which contains synthesized hydrocarbons. As you can see in the table, there is an annex for every approved fuel, and it's important to know that the most common, because of they are being producing in huge quantities or bigger quantities than the other, are Fischer-Tropsch, Annex 1, and EFA, hydroprocessed esters and fatty acids. They can be blended with fossil fuels up to the 50% in volume for the moment. And it's important, the most important thing to know is that any fuel which follows this standard, ASTM Delta 7566, can be treated without any distinction as the one before, as this one, that covers Jet A and Jet A1. And in the military area, we have many regulations. Every country has their own, but we have a NATO Common Guide specification, is the STANAG Standard Agreement 3747, which covers many fuels, including F-34 and F-35. As you can see in the table, for those who are not familiarized, F-34 is the same than Jet Propulsion 8. Is the most common for us, is what we use every day in the F-18. And F-35, which is covered as well, is the same as Jet A1. This is the most common in civil aviation in Europe. So, because in USA they use most Jet A, but they are quite similar. And the difference between this F-34 and F-35 basically is the military. We added a military additive package, which includes a static dissipator, lubricity improver, a fuel system icing, and additionally you can use antioxidant, but it's not a mandatory. Then we have the most important regulations are UK and USA. The UK is important because covers much more fuels, apart from this 91, DEF standard means the defense standard. 91087 covers F-34, there is one for each kind of fuel. But it's important to know that they include all the annexes from the civil, the ASTM Delta 7566. And they include co-processed as well. Co-processed is not exactly e-fuel because it's another kind of technology, but help us to reduce emissions. It's basically vegetable oils, hydrotreated vegetable oil are mixed with crude oil before going to the refinery. But the refinery is exactly the same, so they are not proper e-fuels. And the blending is up to 5%. Only. In the USA, we have the military detail 83133, which covers both F-34 and F-35, among others, but only includes two annexes, EFA and Fischer-Tropsch, the most common. Last but not least, we have the Spanish one, Norma Militar Española, the Spanish military regulation, 3004, which covers the F-34 and is being revised currently just to include EFA, because we are starting to use EFA. We are conducting tests, and we want the EFA to be fabricated in Spain. And our partner Repsol is started this year to produce it in Cartagena, Murcia, Spain. Our Spanish state-of-the-art, as I said, we are conducting tests to include EFA. And last year, our milestone was to get the first approval in one aircraft, was the CASA C-101, the aircraft that Patrulla Águila, the Spanish acrobatic patrol, flies. And we used the co-processed I mentioned before just to do the parade the last Spanish National Day, so 1 year before from now. Basically, it's done for me. Thank you very much.
Sorry again. The Spanish Ministry of Defense is well represented by Captain Cabeza Castaño. Thank you very much for your presentation. And we will also have the National Aerospace Technology Institute, also depending on the Ministry of Defense. They will also have participation this afternoon and tomorrow, okay? And so we will also have the opportunity to know more about the R&D work that the Ministry of Defense is carrying out. And thank you again, Captain. Okay. And now we continue, this time with ITC. Our colleague Santiago Diaz, Dr. Santiago Diaz, he's coordinating the activity in energy planning and also doing coordinating work we are doing on energy storage. So the hydrogen line, I mean the hydrogen projects we are carrying out in the islands are basically coordinated by him, and he will give us show us what we have done, our last hydrogen activity, which is center on this BIOGREENFINERY project, where we are trying to do a proof of concept of advancing in the synthesis of ammonia. We we need to show that's possible to do e-fuels in the Canary Islands, beginning with the excellent resources, both wind and solar resources we have in the archipelago. So please, Santiago, the floor is yours.
Thank you very much, Salvador. Thank you very much, all of you, to come today to this Congress. In this presentation, we are going to explain a little bit the BIOGREENFINERY project. You are going to see the facilities today, too. So first of all, we are going to give you like a little introduction to explain you, mainly for the people that come from other regions, the situation in the Canary Island, the energy situation, because it's important to understand why we think that this research platform is a key element for the Canary Island and the transition that we should do before 2030, okay? So first of all, that is like a general picture that I think that is interesting. Here in Canary Island, we receive every year around 7 million of ton oil equivalents. That is the quantity of energy that we need. We have progressed in the electrical sector, as you could see. In the electrical sector, we are now near the 22% of load demand coverage with renewable energy. However, in the transport sector, we need to do something more because we consume a lot of energy for the transport sector, but the measurements that we are doing nowadays is not enough because we have the electric vehicles, but we need to explore other alternatives like the one that we try to test here in these facilities with the green hydrogen and also other e-fuels that are the ones that we can produce. So in the general balance, nowadays we are in the 2% of the demand coverage of energy, but that is something that is important, the difference between the electrical sector and the rest. So it's something that we need to progress. No? That is the reason why in the energy planning was proposed to introduce this line, that is the line more related to the new e-fuels. No? So you can produce renewable energies in wind farms, photovoltaic plants, etc. No? And try to use part of this energy to produce hydrogen, and after that produce other fuels like, for example, the ammonia or the kerosene, no? For the marine transport sector, for the aviation, for all the sectors. No? So it's a good solution, but should be tested, and should be tested in the conditions that we have in the Canary Islands, because at the end, we are in a region that is isolated. We are not connected to the mainland, but also we are not connected between islands. We have some connections, for example, between Lanzarote and Fuerteventura, 2 of the islands, but not in the rest of the island, and we need to progress on that. No? So that is the main idea why we was designed this project, the one that we are testing here. No? That is only a picture of the power that we have. We have an important penetration in renewable energy, specifically in wind power and solar power. If you compare with the size of the system, we are near 600 megawatts in wind power. In solar power, we are near 300 megawatts. But we have to progress until a big quantity, 1,700 megawatts before 2030. But that is also taking into account the storage that you need for that, and also the hydrogen. That is another way to store the energy and to use in other sectors. Okay. So the green hydrogen, we think that could be interesting in the direct use, for example, for the heavy road transport sector. Specifically because if you compare with other alternatives, for example, the electric buses could be interesting because the time that you need for refill is less than 10 minutes. If you compare with the charging station with 50 kilowatts, is around 12 hours. If you go, for example, to a fast charging system of 150, you need 3-4 hours. So the logistic is worse at the end if you compare with the hydrogen, and that is an opportunity to advance on that. No? Also, we have analyzed the parity of the cost. We think that if we compare with the current price of the diesel, it's more or less 7 kilograms per hour in the current situation. And that is also important. You have all these numbers in the energy planning of the Canary Island, also in the strategy of green hydrogen. So it's only to give you a detail about that. No? And the ammonia is another alternative that is really, really interesting, specifically for other sectors, like, for example, the marine transport sector. The reason is because you can transport that form of energy in liquid in a better conditions. And you have here the comparison. If you want to storage the hydrogen at liquid stage, you need to reduce the temperature until 253 degrees below zero. If you compare with the ammonia could be another alternative. There is other options, of course, but to tell the truth, it's a good alternative and was one of the lines that was selected in this project. No? Regarding the evolution, the things that have been done here in the Canary Islands before to BIOGREENFINERY project, here you have like a map, because most of these projects have been implemented in Gran Canaria until now. One of these facilities was installed in 2007. The REST-2 project was installed in the same location where we have now the BIOGREENFINERY project. In this area, we installed this electrolyzer of 1 kilogram per hour of capacity production. At the next year, in 2008, was installed another electrolyzer to produce green hydrogen for a small car, was another test. Also have been developed different studies regarding how we can modify our transport sector, the heavy road transport sector, to fill only with hydrogen, okay? And also this year, we participate also in a project called Remote, in which a facility also was installed in a cattle farm here in Gran Canaria, in the west area of Gran Canaria. This project participated around 13 companies, was coordinated by Polito, the Polytechnic of Torino in Italy, okay? So that is like the previous project that have been developed. And also, we are here to present a little bit in the past, no? So maybe some of these people, you know them, I don't know. Well, here you have the proof that was here in this year. So we are going to speak now about the BIOGREENFINERY project, okay? BIOGREENFINERY is a project in which we try to demonstrate how we can produce the hydrogen and the other biofuels using as a reference systems in which we have the same situation that in Canary Island. We try to demonstrate how we can produce this hydrogen and other e-fuels using as a reference a standalone solution composed of a wind farm of 100 kilowatts, also a PV plant of around 300 kilowatts. We integrate also batteries in the system, and we have a backup with a biodiesel system. Even the biodiesel that is used for this biodiesel genset is produced in the same facilities as my colleagues are going to explain after me in this presentation, okay? So the project tried to demonstrate how we can produce these new fuels using some demand-side management strategies, and also in conditions that are not maybe the best when you try to work with this kind of solutions. No? So here you have the main components of the system. If we start for the thermical part, we have two electrolyzers. One of these electrolyzers have a capacity of 3 kilograms per hour. We produce hydrogen at 350 bars. Storage in a tank of 60 kilograms in total. And also we have a dispenser to fill 2 cars and a bus. In this, we are going to have real applications. For example, the bus are going to be used in real life here with Global, that is the company that are going to explode the service of this bus. And also we have another line that is more related to the production of ammonia. And for ammonia, you need nitrogen, in this case, and hydrogen. No? So we have a specific electrolyzer to produce 1 kilogram per hour of hydrogen. We store it at 25 bars. Also, we have a nitrogen generator that are going to be explained for my colleague. In this nitrogen generator, we have the capacity to produce around 4 kilograms of nitrogen per hour. And the combination of these two gases can go to the Haber-Bosch to produce ammonia in liquid state, okay? Storing for other applications, like for example, for the marine transport sector. No? So that is a part of the project. Also, there is a gasifier system and other facilities that are going to explain by Celia after me, okay? So that is an important part, but also the supply of energy is quite important too. We have a wind turbine of 100 kilowatts, also 2 PV plants. One of them is of 275 kilowatts, another of 50 kilowatts that is located just in the same area, okay? And the biodiesel that I mentioned before. So if we look in the project in the area, it's like this, okay? We have two main lines. That is the one related to the ammonia. This is the one related to the heavy road transport sector, the use of hydrogen for that, okay? So in the section more related to the green ammonia, we have the electrolyzer in this position. We produce 1 kilogram per hour. We storage in this tank. This tank was the one that was used in the RES2S2 project. We test again the facilities to use again, because it's something important to use the things that we have, and also to check the life of these kind of solutions, no? The nitrogen generator is located in this position, is able to produce 4 kilograms per hour of nitrogen. We storage in this tank, and the combination of these two products goes to the Haber-Bosch. And finally, the liquid ammonia goes to this tank in which we store the product in liquid state, no? Regarding the other line of project, you could see here the other electrolyzer of 3 kilograms per hour of capacity. We store it in 3 tanks, 20 kilograms in each tank at 350 bars. And finally, we have a dispenser system. That is the one that we use to refill the vehicles, no? Also in the same area, we have the biodiesel plant, as I mentioned before. It will be explained later. The biodiesel that is produced by this system, it can be used in this biodiesel genset. So in the same area, we have all the elements that we need. We don't have any kind of connection with the grid. So that is something that is also interesting to test the demand-side management that can be applied and the strategies that could be implemented in real life. At the end, some systems have been manufactured for different companies. The most important thing, in our opinion, is now the integration, how we can integrate that technologies, and also to prepare the strategies to control that in real life in the Canary Islands, okay? Also, in the area, we have different labs to test, because that is a research platform, and also we have the gasifier system in this area. So that is more or less the general structure of the project. Regarding the pipes, you could imagine we have pipes everywhere in all the area, some of them for gases, others for liquids, but in general, we have like 3 main lines. The standard that have been used for the hydrogen is Swagelot. We have 2 pressure, 25 and 350 bars. Regarding the nitrogen, we use systems to connect, of course, the nitrogen generator with also the Haber-Bosch and also the storage system. And for the ammonia, more or less the same. The kind of pipes that we use in both cases, in these both cases, is the same, okay? Don't have, maybe the difference is the hydrogen, because we use a specific standard that is nice and well. Okay, all the systems are integrated in the same grid, in the same microgrid. We have a main board in which we connect all the facilities, the photovoltaic plant, the PV plants that are just in the roof of the system, the battery system, the diesel genset, the wind turbine, okay? And well, maybe the most important thing, or the thing that we like it, because it's called the electrolyzers to apply demand-side management strategy. So with electrolyzers, we can reduce the production from the 100% until the 15% of the total capacity in terms of current, okay? So we can control there the system and try to, well, if we have enough wind and solar resource, we use to apply this demand-side management in this kind of system. No? We use the same protocol for all. We are using Modbus TCP IP for all the system. And also, we design the main control system. We have a human-machine interface solution implemented. Each element have its own human-machine interface, but we also have integrating in a specific solution all the platform, because it's important to control, because in some cases you have experience in other projects, and we have used it and adapted to the hydrogen because we have more experience in battery systems in terms of energy management system, I mean. And it's a little bit different, okay, if you compare with the solution that we implement in this platform. No? Here you have a picture of the PID of one of the electrolyzer, the one of 3 kilograms per hour. The one of 3 kilograms per hour is an alkaline electrolyzer, so we need a purifier. The quality is not enough, and we need to improve with that. So the purifier needs a hydrogen generator, and the hydrogen generator needs an air compressor. So inside the container, you will see that we have a lot of things. Okay. Maybe the most important one is the electrolyzer, but also we have in the rest of the area other elements that are quite important too. Regarding the electrolyzer that is dedicated for the production of ammonia is another alternative, that is a PEM electrolyzer. You could see there the elements. We will see after the presentations, but the power is around 50 kilowatts. The other one reach until 250 kilowatts, more or less. Okay. Also, as I mentioned before, we have the tanks, the 3 tanks and the dispenser system, and the end use, because at the end, we want to test that, stressing the system, doing the same that they are going to do in the real life. So we need a bus. We have bought a bus inside this project, and also 2 cars that you could see at the enter of our facilities. And well, they are going to work. And that is the reason why we think that the tests that we are going to do here are going to be real, are going to be useful for the Canary Islands, and also for the Spain and Europe and wherever. No? So that is all from my part. Thank you very much.
Thank you, Santiago, for briefing us on the BIOGREENFINERY project. Anyway, we will have the chance of visiting after the next presentation the facilities, and we will also have Santiago there to answer some doubts that we might have. The important feature mentioned by Santiago, the fact that the system is working totally isolated. It's a standalone off-grid system. There's no grid connection, and we have the challenge of trying to manage variable and intermittent wind and solar generation. We do it through the energy management system, doing demand-side management, and Santiago pointed out, and also we rely on batteries, lithium-ion batteries for energy storage. And what we have been seeing and proving by suffering is that the system, the hybrid system, hydrogen batteries are always the best choice. I mean, it's not whether it's hydrogen, whether it's batteries, but I think hybridizing the storage of hydrogen with batteries is always a good solution. And so this is a total hybrid system. We have wind, solar, we have the backup, we're backing it up with biodiesel, so which conceptually is a renewable energy, so it's 100% green hydrogen, green ammonia. And Celia will now tell us the second part of the project, having to do with these thermocyclones for the ammonia production. Dr. Celia Bueno, well, she's a PhD in engineering and also a master's in business administration and applied data science. Her PhD work was done on a very interesting project we also have here in the Canary Islands, in the island of El Hierro, the reverse pump hydro system of El Hierro, which is allowing renewable energy penetrations in the island now of 62%. In 2019 was a very good year. And Celia is also supporting, collaborating with Santiago. Santiago is doing energy planning at the regional level, but there's this vision of the European Commission that you have to think globally and act locally. When we talk about acting locally, we have to think of the 88 municipalities of the Canary Islands. And Celia, she's doing work there with the SECAPs and also emission inventories, no? But well, today Celia is not going to talk to us about energy planning, but just about the BIOGREENFINERY project. Please, Celia, the floor is yours.
Thank you to all to come here to know more about the BIOGREENFINERY. Welcome to all. There are two parts in the BIOGREENFIN, that is the production of the hydrogen, and then the production another e-fuels that I want to speak. I want to speak about the. This is the same slide that introduced Santiago, my colleague, but I want to speak about the generation of hydrogen, nitrogen, then the Haber-Bosch. Here is the diesel, the ammonia tank, and the output of this ammonia end use. And we talk about two of the biodiesel plant and a laboratory that we have to measure this composition of ammonia to the with purity, and the gasifier. Here you can see the same slide of Santiago, where I can explain all the rectangle, the color rectangle. Okay. The nitrogen production. The nitrogen, the production began with the air compressors, and then a dryer to this air. Then the line is going to a nitrogen generator with two tanks, and then when we have the 20 bars, we introduce to the end tank. Okay, we produce 40.6 nitrogen kilograms per hour. This is a slide where you can see that is not a prototype. This is here in Pozo Izquierdo, and you can see first at the bottom. You can see the air compressor, then the dryer, the nitrogen generator, and then the two tanks that I say that is for the nitrogen, and then the compressors that produce to 20 bars to the end use tank. And this is the controller that is inside the nitrogen generator, but go to the all controller, the controller of all the equipment. Then when we have the nitrogen, we introduce the two gases the hydrogen that began that come from the first electrolyzers, and the nitrogen with a ratio of hydrogen and nitrogen from 1 kilograms per hour to 40.6 kilograms per hour. And then we produce the ammonia. We have many equipment here because we have a recirculation at the top of the reactor of Haber-Bosch to produce more ammonia, and we have a pretreatment of the gases to preheat, to introduce the gas at more high temperature to the reactor, and then go to the ammonia tank. Here you can see unfortunately, this Haber-Bosch is not here in Pozo Izquierdo, it's and here the reactor, the Haber-Bosch reactor. Then in this slide you can see the line diagram of the Haber-Bosch, and then this is the part of the production of ammonia. Then other part is a gasification. That is not with hydrogen, but is other equipment to produce syngas. Vale? The composition of syngas is e-fuels that with hydrogen approximately 20%, CO approximately 20%, then CO2 and other hydrocarbons. And in this process, we use the glycerin that we produce in the biodiesel plant. In the biodiesel plant that I will go to speak the plant. We introduce this is the reactor of the gasification, and you introduce a liquid as, for example, like the glycerin, and then you have the possibility to change you have in the reactor the same temperature and pressures, but you have the possibility to change the gases to produce the more efficiency syngas. For example, to introduce oxygen, you will introduce nitrogen and other gases to produce more purified or more high production of syngas. Then, at the final, you have a two cyclone and then filters. Who is the why is the gasification here in the project of BIOGREENFINERY? Because we want to produce this syngas to produce another e-fuels, but it's another project for the future. Here you can see the plant. This plant is not here in Pozo Izquierdo 2, but is traveling for here. And then I explain two more parts, the bioenergy lab and the biodiesel plant. The bioenergy lab is a laboratory that we have in Pozo Izquierdo to characterize it. And then with the BIOGREENFINERY, we have three elements, new equipment of three elements. That is the chromatograph to measure ammonia purity, the elemental analysis chromatograph, and a Qatar mill to the catalyst is for the gasification to introduce the waste, the organic waste inside the reactor. And the biodiesel plant. I don't want to speak very much of this biodiesel because it's a trans-esterification, pure trans-esterification process. Only if you want to know that we produce with 450 liters per batch of waste oil with 126 methanol or ethanol, and then we produce the biodiesel of in the proportion of 450, the same as the waste oil, and the glycerin. This glycerin is we use two parts of this biodiesel plant. The first is the biodiesel to the generator grid set, the generator set, jet set. And the other part is the glycerin that we want to analyze introduce to the gasification to produce this syngas. Here you can see the elements. This is the pretreatment. This is the pretreatment. Then the tank. This is the tank, for example, for the glycerin, the water, and the biodiesel. Then in the finish is the. In this slide you can see the generator, the biodiesel generator. That is here in Pozo Izquierdo, and only I have to talk about the ammonia, what we want to use this ammonia. This part is in the interval of beginning, but we want to sell this ammonia to other companies. We have treatment with other companies, and in the harbor or in other use of this ammonia, and this operation close the cycle of the production of ammonia. Thank you for your attention. And if you want.
Thank you, Celia, for explaining the part of the synthesis of ammonia. As Celia mentioned, I mean, what we have is a syngas of nitrogen from there and a green hydrogen from the composition of the water molecules at the electrolyzer that are fed to the Haber-Bosch with an efficiency of 15%. But then you recycle that syngas in a loop in order to get the thing. And then she also explained the other component of the BIOGREENFINERY, which is the biodiesel plant, where we're currently using used cooking oil through a trans-esterification process, as Celia mentioned, to produce this biodiesel, which is allowing us to back up the isolated off-grid standalone system at moments when we don't have enough power from the wind or at nights when we don't have PV, and we have, because we have this, as Santiago also mentioned before, this non-critical, defeatable loads that can be dispatched by the energy management system to optimize. We're talking about the electrolyzers being able to partialize power up down to 15% of nominal power. But then we have the Haber-Bosch reactor that has to be in a steady state because of high pressures and high temperatures, and we have to assure constant supply of power even at nights and moments without wind. So that's when we need to back up with the biodiesel, and also with batteries we have, 400 kilowatt hour of batteries that we also have there. And then what also Celia mentioned, today we have to pay for someone to manage, there's a residue of the process, of the transesterification process, the glycerin, and we are hoping to be able to gasify that glycerin to obtain another syngas with carbon monoxide. In the future, the idea is to go to the synthesis of methane, methanol, and eventually synthetic kerosene. Okay? So thank you very much for this first session. What we are going to do now, we're going for the coffee break, and then we are going to visit not just the BIOGREENFINERY, because our friends from the International Energy Agency, we went yesterday to see the facility, but we will also visit other installations. But, and then we will come back, have lunch, and then the next session will begin at 1. So now we have the chance of having the coffee break and then visit the installation. Thank you very much for participation, and also for the people that have remotely connect through our streaming service. Okay, thank you. Yes, good afternoon. Sorry for the 10-minute delay. For those on streaming, we shall continue then with the second session of today's conference. And the speaker now, Eduardo Lopez, he comes from the National Institute for Aerospace Technology, INTA. It's an R&D institution belonging to the Ministry of Defense, the Spanish Ministry of Defense. And well, Dr. Eduardo, he has been working on hydrogen production for several years. He also very focused on solar hydrogen and also hydrogen storage. Basically, his current fields of activity include energy storage, microgrids, and use of hybrid power systems in vehicles, hydrogen storage, Eurofuel zones. So, Eduardo, please, we should begin because we are a little bit late, and the floor is yours, okay?
Thank you very much, Salvador, and thank you to the Instituto Tecnológico de Canarias for the kind invitation and the opportunity to participate in the inauguration of this very relevant experimental facility at Spanish level and also in European level. Okay, well, the content of my presentation will be related with most of you probably know this information, but it could be a kind of reminder about the different aspects to take into account in the design and the decision about the best different option regarding the storage of hydrogen, pure hydrogen, and also the different options about the use of other compounds, usually liquid compounds, to carriers to transport and distribute the hydrogen from the production site to the end users. Very quickly, facts. Okay, as the previous presentation has shown, for example, the presentation from the first speaker. Okay, there is a lot of importance in European projects regarding the production. In the past, also, mainly from the automotive point of view, and also another applications about the use of hydrogen, but it's necessary an essential link regarding how to transport, how to store before this fuel from the production to the end use. So hydrogen storage is an essential element in the supply value chain of hydrogen. Very quickly, some facts related with the use and the storage of hydrogen. Okay, as you know, hydrogen has a very high energy density per unit of mass, but the situation from the point of view of volume is very different. And that is an important condition regarding how to store the hydrogen for mobile and stationary applications. You know, the hydrogen, of course, is a fuel, but also is an important stock to be used in the industry, and the thermal, also in the thermal generation. Relevant criteria to take into account about what could be advisable in a energy storage system, in a hydrogen storage system, is of course the high energy density. The minimum requirements in terms of equipment and also energy consumption in the auxiliary equipment. Of course, it should be a reliable, safe, and proven technology as far as possible. The minimum cost, the minimum energy consumption in all the elements of the system, the storage capacity without significant loss of hydrogen, and of course the time of refilling and recharging, and the ability to operate in different environmental conditions. For example, in a wide range of temperature, of ambient temperature. That's related also with the key performance in indicators that you can find, for example, in in the technical targets of the USA Department of Energy, and also the technical targets of the fuel cell hydrogen joint undertaking. Okay, regarding the hydrogen capacity, the weight and volume of the system, the cost, the lifetime, the durability, the efficiency, the global efficiency from the charge and until the discharge of the fuel, the rates, the quality of the hydrogen, input and output, and also the environmental conditions. Okay, what is the situation? There is a lot of different possibilities to store hydrogen. We are talking now about hydrogen storage. There is a lot of different possibilities to store hydrogen, but not of them, of course, are able to be used in a practical application, in a practical design and construction of hydrogen storage systems. Okay, from physical basis systems, it's a pure hydrogen as a molecule in compressed gas or liquid form. Okay, to other ways to store hydrogen in material basis. In this way, okay, practical application and commercially available today. At this point, okay, we can use compressed gas tanks in different applications. We can usually use also, depending on the application, we can use the liquid hydrogen. In some small scale application, we can use metal hydride, particularly. And also, as the example we have seen today, it's possible to store or to transform hydrogen in other compounds that can be used directly or to transport and extract later the hydrogen for these carriers. Okay? Compressed gas. This is a typical and usually most used at industrial level at different range of pressure from the high pressure level that we have seen in the dispenser and the refilling station from the ITC, but also low pressure, directly at the pressure of the electrolyzer, to be used directly depending on the final application and the pressure of the electrolyzer. Okay, so there is from the typical the commercial bottle of 50 liters and 8.8 normal cubic meter until the typical tanks for higher production, or even some project, mainly at pilot scale now, regarding the use of varied tanks and pipelines for small scale, but also with a significant hydrogen production. This is for hydrogen for compressed gas. If the production is a large scale, we can consider the geological underground storage of hydrogen. Okay, so there is different possibilities from the oil and gas field, depleted oil and gas field, salt caverns, other caverns, aquifers. Okay, with a wide range of pressure, of volume of storage, but we have to take into account that if we consider only the natural formations, there is some losses that we have to analyze, and other safety requirements and operational requirements about how to store and to use the hydrogen in this kind of storage. Typically, you have seen also the cars outside. So this is in the previous one, okay, we asked using previous experience, because hydrogen in the chemical industry has been used for more than 100 years. The geological storage has been used not for hydrogen, but for natural gas also. These tanks in the vehicles, okay? You know probably the different types, from the types 3, 4, and even the type 5, okay, regarding the increasing use of polymers in the structure. Of course, the scale is limited to the requirement and the needs of the cars and the buses and other vehicles, but it's and the requirement of pressure, of course, came from 350 to 700 bars. Summarizing the potential use, this is a very big picture about the use of compressed gas in different applications. Okay, you can find from the seasonal use in the very long term of hydrogen, very high powers of production in terms, if you can combine the time and the power, you can obtain the energy storage capacity. Okay, and you can find about a theoretical approach, what could be the most interesting option, theoretically, regarding your production rate, your production scale, and of course, the final use of the hydrogen. Liquid hydrogen, okay. In the same way, liquid hydrogen is not new. It has been used in some industries, mainly, for example, in the aerospace, okay, with a long tradition, and there is a long experience regarding the use of this cryogenic liquid. The liquefaction is a minus 253 degrees, and that involves not only a complex design of the tanks, but also a careful handling on the different procedures to use and to handling this fuel. One of the main aspects to be taken into account is that even in the best case, there will be a boil-off of liquid hydrogen. There is a transfer of heat with the environment and other process, the conversion ortho-para, and so on. So it's necessary to a careful design with a lot of different isolation measures and technicals covering the vacuum isolation, the multi-layer. It's a complex engineering, but it is used. Okay, a typical example of the use of liquid hydrogen, as I mentioned before, is in the aerospace use in the rockets. This is, for example, one of the biggest vessels that currently are used in the Kennedy Space Center by the NASA for aerospace applications. Other potential use techniques to store hydrogen are the material basis. They can present some advantages regarding the direct use of hydrogen as compressed gas and liquid, because it's possible, in this case, we store the hydrogen in the forms of atoms that can be combined, chemically combined, absorbed in some structure. It is possible to achieve a very high energy density in terms of volume, okay, hydrogen and energy content per unit of volume. But on the other hand, we have to a material where the hydrogen is integrated, and that means that the energy content, the specific energy, usually is very low. So this the different possibilities. Of course, we have also to take into account the reversibility of the reaction. We have some reversible reaction, for example, the use of metal hydride, and other non-reversible reaction as the use of hydrogen to, for example, to form ammonia or methanol. And if we need to obtain the hydrogen from these compounds, we need to crack it and to proceed with that decomposition process. From this, but these chemical carriers are also an option to store hydrogen. But we have to take very carefully if you need the hydrogen at the end of the process, or if we can use directly this carrier. Okay, for example, the methanol, or the ammonia. In this case, the methanol is a good candidate because we can achieve a hydrogen storage capacity around 12.5 in weight. The methanol, in the same way we have seen today something about it, can be produced from several routes, from biomass, but also from the combination of hydrogen with CO2 from the renewable resources. And the technology of producing the methanol is very mature. It's a commercial level, and this is also possible to transport it in usually by ship and other transport ways. Ammonia is quite similar to the methanol, but in this case, if the renewable methanol requires the use of CO2 from biogenic or transport use it in the chemical industry for long years with a long supply chain. But we have to take into account in all the process, mainly if you use renewable hydrogen, the safety aspect and the potential toxicity aspect regarding the use of ammonia. It's very quickly some data about the use of ammonia. Other ways, other compounds are the liquid organic hydrogen carriers that are mainly based on aromatic compounds, and that theoretically offers also the possibility to transport, to store, transport hydrogen. In this case, on the opposite that the previous one, the methanol ammonia, is not possible up to now. The direct use of these carriers, okay, so it is used just as a way to transport, to store and transport hydrogen. So it's necessary to a process of hydrogenation and dehydrogenation. Okay, so we have to take into account the efficiency, the global efficiency, and the energy used, and thus the process and the storage, and also, for example, using the shipping, the cost to transport the hydrogen, the liquid carrier with the hydrogen, and the liquid compound without hydrogen in the return way. Okay, the storage is more or less clear, the different possibilities to store, and what could be the best efficiency way to transport pure hydrogen or the chemical compound. It depends. The answer depends on the volume, depends on the distance, depends on geographical restriction. For example, in this case, in an island, it's logical that the transport, if we are an exportation, the plan to export, we will need to use shipping. Okay? And there is a lot of different criteria that we have to design a multi-criteria layer. The cost, of course, and other technical requirements, for example, the use of liquid hydrogen depends on the distance regarding the boil off and the potential losses. Okay? But theoretically, you can use for the transmission, the shipping for the liquid hydrogen, for the liquid carrier, for the methanol, tracks at a different level of distance you can use for compressed gas, for liquid gas, for liquid hydrogen, for liquid carriers, and pipeline. You can use pipeline mainly for compressed gas, but also for ammonia, and also in short scale for liquid hydrogen. For example, regarding the long distance, there is some previous experience in the USA and Europe about a significant network, about 5,000 kilometers of hydrogen pipeline. of course, this is for industrial uses. We have to change totally for the new structure, a new network for the energy uses and the requirement for the energy transportation. Okay, in our Spanish level and also on European level, you can find the development of different backbone regarding the hydrogen network infrastructure. Also, the blending with natural gas can be considered, but it's controversial about what could be the real effectivity of this measure as a transition measure or not, or go directly to the development of the hydrogen network. Different criteria. Also, the trucks can be used in interesting use mainly for liquid hydrogen, very good in this way. Ammonia, as I mentioned before, can be used also in pipeline and trucks. There is a very, very long experience. And that's all from my side regarding the structure and the storage. Thank you very much.
Thank you, Eduardo Lopez from INTA. Very interesting briefing about all the possibilities the hydrogen offers for energy storage. He told us about physical things that you could do with hydrogen, from blending to liquid hydrogen, compressed at different pressures. And also, he mentioned the thermocycles running on green hydrogen. For example, ammonia, methanol, possibilities of using also these sort of solutions for overcoming some drawbacks of having hydrogen at too high pressures. So try to make the logistics easier. No? So Eduardo, thank you very much. At the end of the session, if anyone has a question for the speakers. No? And now, after Eduardo, is the time for Paul Luches. Paul Luches is from the French Alternative Energies and Atomic Energy Commission, CEA. He's the he's currently chairing the International Energy Agency in the task of Hydrogen Technology Collaboration Program. He's an international expert on hydrogen and energy systems. He has been participating in many international organizations, European programs. Was a former deputy director of CAP Energies, did I pronounce correctly? And he led many years the R&D program of CEA. So please, Paul, the floor is yours.
Thank you.
Yeah, we're running a little bit late, Paul, because we didn't manage to begin on time. But no, I mean, you have 20 minutes for your presentation.
Thank you very much.
Okay.
Thank you. So, as you know, we are several colleagues here from the Hydrogen TCP, and I think my colleagues after will make some presentation. So, in fact, I changed the title of the speech. I don't know if you remark in the program, because I think the initial title on the European program, it was covered this morning. So I don't want to make overlap. So I changed to the, no, there is something cut, okay. I changed to the more the international collaboration. Why we need international collaboration, not only at European level, but between countries. So I start very basically from the goal. So, you know, we have to abate a lot of gigaton of greenhouse gas, not only CO2, but also methane, because, for example, agriculture is responsible of 25%, not only the famous 75% of CO2, and in different sectors, and it's a huge challenge to go to net zero. And if I take as a starting point the scenario net zero by 2050 from IEA, we have a lot of things. If we want to succeed, we have a lot of things to combine. There is no unique solution. We need to use every technologies, including, of course, renewable, because renewable will play a very big role. You can see on the slide that from quite zero now, solar will become very important as 20%. It's a huge part in the energy mix. Now it's a 0.5, I don't know, something like that. at the world level, etc. So renewable will become very important, but also nuclear in pink as a whole, because it's supposed to at least double, even it's not so large as the renewable. CCS we have to implement, energy efficiency, direct air capture, electrification. So all the technology, all the process we have to combine if we want to reach net zero, with the assumption that in 2050 we will be 2 billion people more. So you can imagine that in one hand we will need more energy, but as we have many energy efficiency gain, we can expect that the level of final energy consumption will be the same as now, despite the economic growth, despite the 2 billion people more. So it's a very ambitious challenge. So we need everything. Without research and innovation, we will not be able to reach. And second, I will detail, because it's a topic of my speech, we need also international collaboration. Without international collaboration, we will not be able to reach net zero. So just this slide on innovation. In fact, if we want to reach the goal by 2030, in 8 years, we have the technology ready for that, more or less. 80% of the technology are ready, are mature. But for 2050, you can see on the slide, now there is an update from IEA, it's maybe not 50%, but maybe 45%. 45% of the technology we need are not mature today. 45% of the technology we need are not mature today. It's the reason why we need a lot of demonstration, we need a lot of acceleration of maturation of technology. And you can see here on the slide, it's taken from IEA report, of course, hydrogen-based steel, small modular reactor, for example, synthetic fuel, you are in the middle of that, etc. And not every technology is mature. On direct air capture, of course, we need direct air capture, but we know it's too expensive now. So my message was we need more R&D, more public funding, private funding on R&D, on innovation. But the second one, maybe it's a question not very well known, why we need international collaboration. In fact, this slide shows that if we don't have a very high level of international collaboration, you can see the slide, the net zero will be reached, but not in 2050, but in 2000. And so it's a result, and why we need international collaboration. We have an initiative called Breakthrough Agenda report every year, collaboration with IEA, IRENA, and United Nations. There is different reason. I will try to explain in detail. We need international collaboration. First, it's not by order of priority. It's just different reason on international collaboration topics. First, on the standards, certification, I will speak after an example on that. If you want to develop the international trade, for example, of hydrogen or for ammonia, we need standards, we need certification scheme. And you can imagine that by nature, we need agreement on international level. Without agreement, for example, the import country will never trust what's happened in the export country. So we need international collaboration on standards, on certification. So second, for example, to create market creation and stimulate demand, we need a collaboration on the incentive to stimulate the demand. Not only in one country, but a coordinated action for the demand. Another priority, we need also to collaborate on R&D and innovation, because a lot of countries, for example, they don't have enough demonstration projects. So we need to share the knowledge. We need to help some emerging country, or at least less developed country, to increase their capacity building, for example, to transfer technology in some sense, etc. So we need also international collaboration. We can also gain economy of scale if we coordinate better the deployment. Of course, infrastructure in some regions are very important. For example, between Africa and Europe, we need also to coordinate the infrastructure development. And another very, very important reason is about the finance and the funding of the energy transition. The IEA shows that we need to multiply by 4 the level of investment today, which is huge. Today, we have a huge investment in new technology, but it's not enough. The pace is not enough. And for that, the problem of, because public investment is one thing, but we need to leverage with private investment. And you know, the main issue is the risk. Risk means interest rate, etc. And if there is a lot of projects not bankable, it's because there is a high risk for the investor. And so if, for example, initiative from the World Bank or international assistance on finance could coordinate a program, it could de-risk the investment. So it's another reason for international collaboration. And I said capacity building, share knowledge, etc. So we need this international collaboration. So if I now focus on hydrogen, because what I said is available for all technologies, of course, you know that I will go very quickly. We know that according to the different scenarios, hydrogen will play a role in the energy transition. I said not only, it's not the only solution, but we need massive hydrogen production and utilization. So I will skip this one. In different sectors, we know that it's very important to hard-to-abate sector in industry, fuel, mobility, and energy grid management. So I think everyone here knows why we need hydrogen. But the immense challenge is scaling up. And, you know, I think it was presented, no, it was not presented today, but we have a lot of projects in the world, but only between 5 and 10% are on the stage of final investment decision. Why? Because there is many different reasons. One is a lack of demand. There is project, but on the paper, but if there is not a contract, the investor will not invest to, I don't know, in Morocco, in South Africa, on hydrogen production. And the second is certification, because we need this scheme of standards and certification. And of course, after we have other challenge for the manufacturing scale up, etc. So, but we have also potentially also other issue on critical material, water consumption. But I don't want to go in detail on that. So now, saying that we need international collaboration, we have existing framework for that. I show you. You can notice that our organization, Hydrogen TCP, was created in 1975. And now we saw, since the last 5 years, a lot of organizations working on international coordination. Maybe it seems a very complex landscape because we have many international organizations dealing on hydrogen. You see, there is a list here. Some are public sector-led, others are private sector-led on analysis, and we work also on certification. Some others, like the World Bank on hydrogen, they are working on how to de-risk the investment on hydrogen. Some others, like UNIDO agency, they try to make the bridge between the developed countries and the less developed countries. So it could seem very complex. It is very complex, but we try to make a certain degree of coherence. And in this perspective, at least there is 4 actions where there is a coordination. I will take just 2 examples to finish my presentation. The first is on a certification scheme. So it is a coordinated action between IPHE and the TCP, our program. And I will show you. So we have, for example, what we call a task in our TCP is a project of 3 years gathering experts, private, public, working on a topic and giving some deliverables. For example, this task we adopted this year will work on the technical aspect because we saw this morning that there is some scheme, for example, in Spain, there is scheme in other countries, in US. We try to establish a platform for a mutual recognition framework. How we think that there will be never one unique system at the world level, but at least the scheme must be coherent between them. So it's an example of what we are trying to achieve on certification, on standards. And the other example, it's not in our TCP, is about the future international trade, because today the trade is mainly on fossil fuel. Maybe in 2050, the fossil fuel will replace, on the international trade point of view, by critical material on hydrogen and derivative, okay? And if we want to establish this new trade, which changed dramatically the geopolitics of energy, because now you have Middle East, we know the problem with the geopolitics of oil and gas, etc. In the future, we will have another geopolitics, and with less business, the business will be smaller than today. And for that, we need to start with cooperation. And just to show you, it is not in our organization, but in the Clean Energy Ministerial, there was the launch of an International Hydrogen Trade Forum very recently to try to coordinate the effort, the action on how to launch this international trade. And I will just finish because I am representing the hydrogen TCP, so just to show you that we are an organization under the umbrella of IEA in Paris, but we are not exactly the IEA. And we are gathering 25 countries, 6 sponsors, and we organize our exco meeting this last 2 days here. So thank you very much to welcome us. And what we are doing is a task. I mentioned the task on safety, on certification, but you see that we have a lot of topics on which we are working. Underground storage, safety, energy storage. Some of my colleagues are here. They are leading some tasks on renewable hydrogen production, etc. I want just to mention, so we have a task in definition, not yet launched, on natural hydrogen. Maybe it could be interesting for Spain. But you see that there is one, it's very preliminary idea on hydrogen in islands. So I talk with you a little, but I think it could be a good idea to work together to launch maybe. I think there is a huge interest to launch a specific task in our organization on this topic. So thank you very much.
Thank you very much, and also you're being so sensitive about the need to progress also in islands, that the islands can also be heard and have a voice in the International Energy Agency task groups working on hydrogen. I think this should be a must. Yeah. Many islands all over the world with high renewable energy potentials and the need for new energy vectors based on green hydrogen. Paul, you mentioned that we would need many technologies that today are not mature, and we need to move fast. No? We need to mobilize investment, funding, the public investment in order to kickstart this demand. Ohiri, am I pronouncing it correctly? Is responsible for the overall strategy, execution, and coordination of NEDO research, working on fuel cells since 1992, was it? Yeah. And he's a graduate from Tokyo University of Science, and he was also at MIT, at the Massachusetts Institute of Technology from 97 to 98. So please, Ohira, the floor is yours to tell us Japan's current activity, including renewable energy, renewable hydrogen, and hydrogen valleys.
Yeah. All right. Thank you very much for the kind introduction. Well, I'm Eiji Ohira. I'm in charge of the hydrogen fuel cell program. I'm very happy to be here. It's a very beautiful island. It'll be the first time here. Anyway, and let me start. And what is the NEDO? The NEDO is a kind of a funding agency, and the Japan mostly to the industry. We didn't have any research function. We promote national R&D project, and collaborate with Japan and the industry and the university and the public institute. One of our big role is to develop the kind of direction how of the future image and organize and the best team to promote an R&D. Well, and we have the history. We established in the 1988. It's mean we have over 40 years history. But in Japan, before our establishment, in Japan started a national project for the hydrogen production in 1974, and we have over the half century in the histories. But after the 50 years, we just now to the front door to the hydrogen-based society anyway. And today I'm bringing information about Japan and the policy and the current R&D activities. So let me start Japan and environment situation, especially the carbon dioxide emission. Well, this is the CO2 emission for the energy sectors. Well, you may say that the CO2 from the power sector just account only 40%. Yes, in Japan, to try to enhance the zero carbon electricity like renewable and nuclear. So our target we can be 40% for renewable and 20% nuclear in 2030. But it's not enough for the carbon neutrality because we need to address the other sector like industry, transportation, etc., etc. That's why we promoted the hydrogen. And I think that Japan is the first country to develop the national hydrogen strategy, the leadership of our prime ministers. Well, and this is the first version, an image of the first version of our hydrogen strategies, and published in 2017 December. Well, and this is to the vision toward 2050 to meet in the Paris Agreement minus 80% decrease of the CO2 emission. And also we set the midterm target on the 2030 target on number of the fuel cell vehicle, hydrogen filling stations, etc., etc. Well, and our future ultimate goal is to develop the enhanced hydrogen bound 2050 and reduce the hydrogen cost, not only hydrogen production, also the hydrogen transport cost, and to meet in almost same as the cost of natural gas for the power generation. I mean, the cost parity for the natural gas in 2050. Well, but after the 6 years, the Japanese government and the government of Japan just revised our hydrogen in the strategies. Well, this is I just pick up the point of the new version, and the first one we set a new target. As I mentioned before, we have the we have the hydrogen demand target in 2030. It's 2 million tons, 3 million tons, and 2050 target, which is 20 million tons. In addition, we set a 2040 target, which is 12 million tons. And also they were recognized on the importance of electrolysis for the low carbon energy systems. Well, I suppose it's a very ambitious target, but we set on the 15 gigawatt and electrolysis, not only in Japan, but globally, but not only in electrolysis itself, but also including the kind of the materials, any parts, and any kind of the business. I mean, the 15 gigawatt is going to be not only hydrogen the production, but also any other related technology. But we'd like to expand in our activity globally. And the second point is Japan to promote low carbon hydrogen, and with the definition of low carbon hydrogen, and we don't care about the color of hydrogen. Yes, in a lot of countries you need to promote the green hydrogen, but in Japan, green hydrogen is very limited. So we like to promote low carbon hydrogen, the definition which is below 3 kilogram CO2 emission while to producing the kilogram and the hydrogen. It's one of the definition. And also, we say other issue is the new strategy is not only energy and environment, but also industrial strategies. Well, we expected a huge amount of investment in this area such as 15 trillion public-private fund from the international global supply chains, which including the for contract for difference. It's kind of the subsidy, so reducing the cost gap, price gap between fossil fuel and hydrogen in the short term. And also the DOJ and sector prioritize new technology to be disseminated globally, which is electrolysis, hydrogen supply chain, gas turbine, or fuel cells. And this figure shows the kind of rough roadmap toward 2050. You know, the cover and the area covered by hydrogen and quite wide. And we had a lot of action for hydrogen production, storage, transport, utilization, and a lot of activity in the short term, mid term, long term. But I would like to stress the year 2030, and it's a very important year for us in Japan, because we understand in the hydrogen and power generation by partially or 100%. Anyway, but we may install the hydrogen power generation. They will start in 2030. And the hydrogen power generation need a huge amount of the hydrogen supply. So now we start in the hydrogen import and then in the 2030. To expand in the domestic hydrogen source, so they would like to commercialize and a social system like regulation, code and the standard and the certification that Paul mentioned about that. Well, and this is the current status of the hydrogen fuel cell application. Japan's success to launch in the world first and the mass scale and high fuel cell production, which is stationary residential fuel cell, namely NFM, is the natural gas-based and a kind of combined heat and power system. And we have the almost 500,000 units already installed in Japan's household. But it's a very small unit, just providing 700 watt, 0.7 kilowatt power, and also providing the thermal heat, maybe, and hot water. And on mobility sector, then Toyota already launched the Mirai, the second generation Mirai, and we have the 7,000 fuel cell passenger vehicle registered in the Japan market. And fuel cell dominant berth, it's including the 200 kilowatt and Toyota fuel cell stack. And in Japan, we have the 120 and the fuel cell buses, and mainly running in Tokyo area regularly. You may see the fuel cell buses, and so very frequency in Tokyo area. And the power station and the hydrogen filling station, they're key to disseminate the fuel cell vehicle. And in Japan, we have the only the 700 bar commercial station, and we have the 160 in globally, and nationwide, mainly in Tokyo and Aichi Prefecture. It's the hometown of Toyota. Well, and next I would like to talk about NEDO's activities, and with 100% fund from the METI, we are conducting several projects, hydrogen production. So we make the fuel cell name of the fuel cell more familiar to the Japan people. When the second step in the fuel cell vehicle and hydrogen filling station, when the and the fuel cell vehicle, it's in the first application to use the hydrogen itself in a city area. Well, to use the hydrogen safety, we need to develop the hydrogen infrastructure, the production or distribution, and including the hydrogen filling station. We also need to develop the new regulation code and standard for the fuel cell vehicles. When the third step, so we need to develop the expand and the hydrogen demand. The challenge is how to integrate hydrogen to the energy existing energy systems. Well, and let me talk about kind of snapshot from the current Japan to activity, R&D activities. Well, and yeah, we have the fuel cell vehicle and the fuel cell buses. When you try to expand in the commercial vehicle developed a huge amount of the hydrogen demand. or increasing the capacity factor of the one single hydrogen filling station. And because they come to the fuel source and hydrogen filling station in regularly, in the morning and nighttime. It's very scheduled. Anyway, and through the demonstration, we installed the 300 and fuel cell commercial trucks, and which heavy-duty truck and light-duty truck. In the other application, also the other application for material handling, it's large-scale material handling, especially in the port. Also, they're working for the maritime application and the fuel cell ship. It's going to be launched in 2025 and in 2-3 years. Well, to install the commercial heavy-duty vehicle, we need to develop the high-speed hydrogen fueling technologies, right? But now we have current technology in, how can I say? Well, and 5 kilogram hydrogen in 3 minutes. It's kind of the global regulation for the passenger vehicle, but not enough for the commercial vehicle. We need to develop the 80 kilogram hydrogen in 10 minutes. Right, it's very high speed, high amount technology. And we already developed the kind of technical center for the hydrogen refueling, and we are testing the several refueling and measuring the technologies. Our idea is using the middle flow and dual develop enhancing the hydrogen demand, and we make a small size. And we're already working for the small size, megawatt scale, the hydrogen gas turbine is developed by the Kawasaki Heavy Industries. And the light one is we're just working for the, I can say, and hydrogen and combustors. And our idea is to retrofit it and so install the hydrogen combustors for an existing power station like this, just replacing the combustors. So maybe to reduce the costs for installation. And that's my idea. Well, and we already developed the hydrogen combustor. Now our plan to install the existing power station in 2025. And the first step is 30% hydrogen power generation. And also we try to make it 100% around the 2030s. Well, and in the future, a big challenge is how to concentrate for our hydrogen transportation. We choose 2 types of the hydrogen carrier. One is the organic chemical hydrate, and that's one liquefied hydrogen. We already developed our first small but our first liquefied hydrogen tanker, and our first and second journey between Japan and Australia completed successfully. We would like to expand it to the commercial scale toward the 2030. We finished the feasibility study and identifying the exact place for hydrogen and the production, the hydrogen receiving, and development will start into next year. Well, and we're sort of working for the scaling up electrolysis and PEM electrolysis and alkaline electrolysis at the megawatt scale. The right one is alkaline electrolysis at the single stack, and at 10 megawatt, we can produce 2,000 normal cubic meter per hour and the maximum. Using the green hydrogen, we provide it in Fukushima prefecture. And that the nuclear accident occurred in this. They changed to nuclear to the renewable-based society, and they may install the several and fuel cell application, fuel cell or the hydrogen application, stationary fuel cell, and refueling station or industry uses. And combined with renewable hydrogen and this hydrogen demand, we'd like to develop make the Fukushima as a hydrogen valley. And also the working for the outside Japan, we may install and fuel cell application at port, collaborate with the port of Los Angeles, so to contribute to decarbonization and air pollution. Through the activities combined with renewable hydrogen, renewable gas hydrogen, and the mobile refueler, we verified the usability and the fuel cell application compared to the existing gasoline or diesel application. Right? So and just a short presentation, not short presentation. That's all the current activity. Thank you very much for you. Thank you.
Thank you very much, Hira from Japan NEDO. Well, you have shown us the very ambitious goals that the hydrogen strategy includes, and and the elements of this very comprehensive strategy. Also, I mean, talking about 2030, you're talking about multiplying by 10 the current bus fleet and by 100 the current car fleet. So this is will mean a big effort in Japan, but Japan it's definitely betting on hydrogen, and the strategy even talks about importing hydrogen into Japan for this purpose. So Hira, thank you very much for your presentation. Okay? The next speaker from Australia, Robert Dickinson. He will talk about hydrogen modeling in task 41 and a case study. Robert, well, he has experience on software development, system design engineering, been working in Canada and the USA. He launched Hydricity Systems as a division of Data Space Insight in 2008. And well, he has been working on hydrogen energy before it has become among the mainstream. Well, he's currently participating in Task 38 of Power 2X of the International Energy Agency, the TCP, and also on the modeling in Task 41. So, Robert, the floor is yours, please.
Okay.
No.
No, yeah. I'm not sure where the second title came from. That's what's in your program, but whoever wrote it, that's pretty accurate, as it turns out. Just a long-winded way of saying the same thing. Yeah. Can I use this instead? Yeah. So just 5 really quick slides, pretty much an introduction to what Task 41 has been about. A very quick mention of the data outlook of Task 41, and then I'll focus on a quick mention of a couple of other things from Task 41. But I'd like to make sure I've got time at the end, because I wrote the slides for that last step on the airplane on the way here, and it's been quite insightful to see what's actually here, and I've got lots more to say having been here. So these are all the people that contributed to Task 41. This is Task 41, for those who don't know, was one of the many tasks that Paul Lucas was talking about in the previous talk. So you can download that off the website. Just go to iehydrogen.org, and it's currently on the front page of that. But this is all of the sections that I've talked about in the past. One of the original motivations for Task, or probably the main motivation, was that there was concern that the modeling that had been done prior to sort of mid-2010s was not capturing the value of the opportunity for hydrogen as well as it could be. So there was an objective to look at other ways of modeling as well as improving the existing ways of modeling. But so we, as Task 41 at the bottom there, we can't take credit for all of these steep curves because they're happening anyway. What's driving all of this steep increasing in interest in hydrogen modeling is climate impacts. They're here now, everywhere around the world. We've got major floods in Europe and bushfires in northern Canada. Australia has both. In regions that didn't have flooding, didn't have, some parts didn't have bushfires either. So, yeah, lots of drivers for increasing the depth and breadth of the way we do modeling. And then historically, Task 38 was a predecessor. I've been involved in that, and Paul was involved in that. I think a couple of other people here might have been. And it's, as you can see from the 2019-2020, hit the end of pandemic, and Task 41 started just prior to the pandemic. So as it turned out, all of Task 41 was done virtually. We didn't have any in-person meetings. So that was a huge challenge, because that's one of the really cool things about my traveling all the way to Australia is you get to, there are a lot of advantages of in-person meetings. So we didn't have any of those advantages, but we managed to get by and produce a report at the end of the day. And one of the other things, as well as those steep curves that we saw a couple of slides ago, the IEA, I'm not sure who's here from the IEA, it's above the IEA hydrogen TCP, was not as engaged in hydrogen as the IEA hydrogen people thought it could be. And it turns out there wasn't much in the way of reports prior to, can you see this? Yeah. I put a question mark there because I wanted to invite IEA people to say, is there anything that I can put in there in the way of a report? And it turns out there wasn't. So really, things really started to pick up with the G20 in Japan. The rest of you probably there. And then the first Global Hydrogen Review in 2021, another one last year, and then a brand new one just a couple of weeks ago this year, and then some renewables. So things are really, interest in hydrogen at the top level of IEA have really picked up big time, which is really good news. About data, I'll cut a long story short, I'll just look at the end point of what was a year and a half of work on data. In short, the Hydrogen Council and McKinsey already publish a lot of data that is useful to the entire hydrogen community and most useful to the members because they get data that we can't see as the public. And there's a large number, as you can see there, a large number of private companies that already invest in the Hydrogen Council. And so I've suggested what I call Hydrogen Insights plus. So take the same initiative of the Hydrogen Insights and add modeling data specific to modeling. So what do all the modeling people need in the way of data to be confident that heard the expression garbage in, garbage out. Good data in hopefully means good data out. So yeah. And I just refer to data clean rooms because that was used in the critical minerals report to get data that you can't get otherwise. Model taxonomy, I'll skip over that because at the end of the day, we came up with 9 archetypes or categories, if you like, of modeling systems. And the background was a 10,000 word, very verbose paper published in one of the journals. But let's look specifically at islands, one of which is Gran Canaria. So I mean by an island, I mean a region that doesn't have any connectivity with the outside world, except perhaps importing fossil fuels. Let me fill off the chair. So the advantages that it has is that it can realistically, because it's a confined space, realistically talk about modeling 100% renewable energy in the long term. In other regions, you might have to make a lot of assumptions if you just wanted to get towards 100%. Challenges there requires a lot of potentially seasonal storage, although the weather here has been pretty flat for the last 3 days. I don't know if it's like that throughout the year, but I'll come back to that in a minute. And requires high temporal resolution. I've put here 5 to 30 minute dispatch periods. I'm not sure if we've got a grids person here that can confirm. It's probably 30 minute dispatch periods here, I'm not sure. And then I've said limited prospects for two-sided price dynamics modeling. I'll describe what that is, and then if anyone wants to suggest that maybe it's not that limited, maybe you can do it here. We could talk about that, but that's just a bunch of, for all of the UK or whatever, they have this thing called ETSAP. ETSAP, for those who don't know, is another technology collaboration program. So you got the IEA at the top, ETSAP and the greenhouse gas people and a bunch of others, and IEA hydrogen. So we've had these ETSAP people, and they've been around for a long time, but have not been having as much impact on the IEA as we'd like. So, anyways, yeah, but that's complicated. And again, if you look from the left-hand end is the inputs, and that flows all the way through to applications on the right-hand end. So let's have a look at Gran Canaria. No, that's not bad. Yeah, it's perfect. I might spend 5, maybe, we'll see how it goes. On this one, so this is from the PTE Canary. So you've got the island of Gran Canaria. I guess there's no electricity on the west coast, is that right? Or no grid electricity anyway. And the crux though from the process of my talk is currently there's about 20% of variable renewable energy. So tiny. The current situation is 20% VRE, as I said in the previous slide. And the modeling for PTE CAN has it going up to 2030 has it going up to 60% by 2030. So that's a big jump, it's 3 times. Nevertheless, I thought it'd be interesting to look at it going even further. I'm going to skip over that because I want to focus on what it's going to take to get up to 100%. Anyway, you can read that for yourself. You get a copy of these presentation files, I presume, at the end. Just very quickly, this is South Australia. It's referring to the two-way price dynamics that I alluded to and saying that it would be hard to do that here because of the way the market is set up. So I'll just say that that possibility exists, but I need to learn more about how your electricity market is set up in terms of 5-minute dispatch periods and whether there's really a bidding system for generators right now. And if that doesn't exist, then there's no point in talking about a bidding system for the demand side either. But yeah, so in summary, the PTE CAN looks great. I think it'd be interesting to look at a few other things, but the most important thing for me, I'm already running out of time, but what would it take to get to over 100% between now and 2050? It's easily doable as far as I'm concerned. So what? And this is where I stopped on the airplane of writing this thing. But so let's look at a few things. There's no rooftop solar in Gran Canaria, so far as I know. You'd probably get somewhere between 0.5 gigawatt and 1 gigawatt just by saturating rooftop solar. Right now, rooftop solar causes, in South Australia, causes prices to go negative when there's no demand in all of the residential places that are not consuming because they're generating their own solar. So that's easy to do, but it's not very large. Much bigger one is wind. You've already got 20% wind. If you wanted to go 5%, you've got 100% just with wind alone. And then you've got to deal with the excess, and that's where it gets interesting for hydrogen. Whether you use a market for power to hydrogen or some other mechanism that's the role for hydrogen. So what would it take to do 5 times wind power? When you look out here, there's a sea of small 225 kilowatt wind turbines. The largest turbine in the world at the moment, and it's just continuing to get larger and larger, is 16 megawatts. So that's you can take 70 of these things out here, and you've got one of the largest in the world. Admittedly, that one of the largest in the world is going to cost a lot more than one of these, but it's a lot less than 70 times one of these. So the cost effectiveness of going up to get way above the boundary layer, it's just that's what's driving the scale is to get way above the boundary layer. Another way of getting above the boundary layer is for me most of these turbines should be up on the ridge. I don't, if there's any reason why you don't have 20 years from now lots of large-scale turbines on the top of the ridge, then I don't get it. There might be a reason for not doing that, but I don't know. Another one is, I've probably run out of time, have I? Yeah, anyways. The other big thing is the turnaround efficiency of power to hydrogen to power. Everyone here knows it's around 30%. Really optimistic might get up to 80, after 40, 45%. That's still really low relative to pumped hydro. Pumped hydro is you use electricity to spin the pumps to push it up the hill, and then when you want to generate power, you let the water go down the hill. You got huge elevation changes. As far as I know, there's no environmental reason to not have very large-scale pumped hydro. It doesn't have to be certainly doesn't have to be potable water. It probably would be better to be fresh water, so desalinated, as you've already got. And you're just going up and down, so you desalinate once and then you use it up and down. So yeah, it's, and you don't have to have rain to do pumped hydro. You have to have rain to do hydro. I just got the 5 minutes.
Thank you, Robert Dickinson from Database Insight in Australia. Well, Robert told us about the work that he has been performing in Task 41 with the Energy Technology System Analysis Program applied to the case study of Gran Canaria. Yeah, we appreciate that you have done that work for the island. And well, what Robert tells us is that he thinks that more rooftops are needed in the island, and when you consider options like hydrogen round-trip efficiency compared to reverse pump hydro, probably the second alternative is much cost-efficient. Yeah, well, yeah, right. The ecosystem is complex, and you need all technologies. Thank you, Robert. Okay, and now we have a second Robert. No? And the second Robert comes from Pittsburgh, from the U.S. Well, he's originally from Pittsburgh, but his heart is in Connecticut, no, Robert? So Robert comes from the Department of Energy, and well, he's an engineer from Carnegie Mellon University, and he has been before beginning at the Department of Energy. He was for 13 years as a boiler R&D program manager for GE Steam Power and for Alstom Power in Windsor, Connecticut. Has been also for more than 38 years working on fossil power research technologies. And well, Robert, the floor is yours. Please.
Hey, thank you very much for the kind introduction, and thanks for the opportunity to speak here at the inauguration of the BIOGREENFINEry at the Instituto Tecnológico de Canarias on beautiful Gran Canaria Island, a great venue for a conference, I must say. So this slide, I was to talk about the hydrogen roadmap in the United States and then our work on biofuels and e-fuels. So rather than delve into this hydrogen strategy and roadmap, which is a very dense, very comprehensive document, you can scan this QR code up here, download it to your phone, read it at your leisure, help you sleep at night, whatever works for you. So rather than a death by PowerPoint presentation here today, I'd just like to highlight some of our recent awards that we've made in the hydrogen and decarbonization space, and also to tell you a little bit about the research we're pursuing on utilization of hydrogen and hydrogen carriers such as ammonia, e-fuels such as sustainable aviation fuel. As you all may know, the U.S. embarked on an unprecedented, historic, all of the U.S. government effort to meet the global climate challenge. You can see up here multiple applied energy offices are involved, the Office of Energy Efficiency and Renewable Energy, my office, the Office of Fossil Energy and Carbon Management, the Nuclear Energy Office, plus all the others, EPA, Department of the Interior, Geological Survey, so many agencies involved in the U.S. It really takes this comprehensive effort to meet the goals set by President Biden of a 30% or a 50% reduction in electricity emissions by 2030, a totally green electricity grid by 2035, and a net zero emissions economy by 2050. So really central to this effort is the funding and financing provided by the U.S. Congress in the Bipartisan Infrastructure Law. We're coming up on 2 years ago now that Congress authorized $62 billion for the Department of Energy to focus on all the above technologies. We're looking at electrolysis, we're looking at carbon management, we're looking at hydrogen, we're looking at all of these. And so that $62 billion is really designed to accelerate the clean energy transition in the U.S. I'm going to give you a couple of examples of awards we've made. We recently made 2 direct air capture regional hub awards. That was $1.2 billion in U.S. funding total for those 2 hubs. The first 2 DAC hubs will be in Texas and Louisiana, 2 Gulf Coast states with very large petrochemical refining operations that a challenge to decarbonize there. In addition to the DAC hubs, we have another 19 awards out that are engineering and feasibility studies for future direct air capture hubs. Successful applicants were anywhere from Alaskan native lands, which we kind of consider as an energy island themselves. They're very isolated and really have to deal with just their own resources there. But we also have them in Wyoming coal country, Florida, and Southern California. So direct air capture is an important tool because it actually addresses legacy CO2 emissions in the atmosphere. We're removing it from the atmosphere instead of not emitting it or trying to capture it before it's emitted. But that's really only one of the tools in our decarbonization toolbox. So as the director of the Hydrogen with Carbon Management Division, it was very exciting to me last week when President Biden announced the historic investment of $7 billion US for 7 regional hydrogen hubs. These are highly leveraged projects, which is a really great thing for the value to the US taxpayers, because with the industry co-funding included, those 7 hubs are actually going to be spending close to $50 billion in total. So like a 6-to-1 leverage factor, very, very effective use of tax dollars. And again, these are support multiple pathways for clean hydrogen production. They include like grid-driven or behind-the-grid and electrolysis, biomass and waste gasification pathways that include carbon capture and permanent sequestration with the goal to achieve net zero hydrogen, and natural gas reforming pathways also with carbon capture and permanent sequestration. So these direct air capture and hydrogen hubs take advantage of the resources available regionally for hydrogen production and carbon sequestration. Right now, the U.S. produces about 10 million tons of, we don't like to use colors, but I'll call it gray hydrogen because it's dirty. Our goal by 2030 in the hydrogen roadmap is to produce 10 million tons of clean hydrogen. These hubs should achieve about 3 million tons of that 10 million ton total. So when these hubs are up and fully operational, we'll have 3 million tons of clean hydrogen per year produced by these 7 hubs. These direct air so I'll just run real quickly through, there's hubs that are mainly renewable based in Southern California and the Pacific Northwest. There's a couple with nuclear components in the Mid-Atlantic states. There's also several that involve a lot of carbon management with the Houston and the Gulf Coast, the Appalachian region, the Midwest, and the heartland, like the very north where lots of coal is still produced in the U.S. and like Wyoming, Montana. So I wanted to highlight the regional aspects of these hubs because that's an additional challenge faced by an island valley like Gran Canaria, where you have only your regional resources available to meet your clean energy goals. So everyone has talked, you clearly have significant wind and solar resources here already. As Rob mentioned, you have the room to expand those a lot more. I'd include offshore wind as one of your expansion possibilities. I see there are a few large offshore turbines along here, and that could be increased quite a bit. But for resilience of the electricity grid here, you have battery storage, but typically a short-term, 4 to 12-hour solution depending on how many battery packs you install. And you need that for when the wind doesn't blow and the sun doesn't shine. So for longer-term backup of renewable energy generation, we see dispatchable power generation assets that are available 24 hours per day, 7 days a week to be required. I mean, I see Monday actually driving to here, we saw the heavy oil-fired plant near the airport. It was running pretty heavily there to generate the electricity. Right out back here, I see you have several combined cycle plants there as well. They run on diesel since there is natural gas that's not available on the island here. Both of these could be decarbonized to support dispatchable backup of the renewables on the island here. But to do that, you're going to really have to clean up the fuels that are used in those assets. And so that's where long-duration energy storage comes in, as Robert was talking about, like seasonal, greater than 6-month storage potential. And I see the BIOGREENFINERY project as a really impressive first step in demonstrating and then deploying clean hydrogen and zero-carbon fuels and feedstocks. So the U.S. doesn't have just government-funded work. There's a lot of private industry work going on as well. I guess our largest long-duration energy storage project right now is called the Advanced Clean Energy Storage Project in Utah. It's partially funded by a $500 million loan from the DOE's Loan Program Office. So in addition to providing grants for projects, we also provide government-backed loans. Some of you may remember Tesla started with a government-backed loan and turned into a very successful commercial company. So the project looks to produce hydrogen from behind the grid or grid-based electricity through electrolysis, stored in 2 large salt domes on site there. They're already under construction, those 2 salt domes. And then they want to fire the hydrogen in Mitsubishi combustion turbines. And they will actually provide backup power to Los Angeles Port of Los Angeles, and the Los Angeles Basin in general. They happen to have the correct geology there for hydrogen storage. So, like not everywhere has that, but it may have a potential for long-duration energy storage here, depending on what fuel you're going to produce for which of your generation assets here. And the fact that the BIOGREENFINERY is demonstrating hydrogen production by both alkaline and PEM electrolyzers, it's really much the same way that we're demonstrating there at this project in Utah. So an alternative to hydrogen storage is the production of ammonia from hydrogen and nitrogen, to use ammonia as either a hydrogen carrier or even potentially as a direct fuel. And again, your BIOGREENFINERY here is demonstrating the production of ammonia. Several people have discussed that ammonia has important advantages, cost advantages when it comes to liquefaction and transportation. And because of that, there's increasing international interest in world trade of ammonia. Last year, there was a ammonia shipment from the United Arab Emirates to Japan, we saw, and to demonstrate the feasibility of large-scale, long-distance transport of ammonia. The U.S. has another initiative called the Clean Fuels and Products Earthshot. We've had several Earthshots announced over the last 2 years. The first one was the Hydrogen Energy Earthshot to reduce the cost of hydrogen to $2 by 2030, $2 per kilogram by 2030, and further to $1 per kilogram by 2050. That will be a very important cost reduction to be able to compete with current fuels. We're also researching direct firing of ammonia in combustion turbines. I discussed that with someone earlier at lunch today. And we're getting really promising results. You would think with the high nitrogen content in ammonia, you would have significant NOx emissions when you burn it. But we have researchers working on rich quench lean concepts for combustion. A typical gas turbine now for low NOx will operate in a lean premix mode, so ammonia actually has to operate in a rich premix mode, which seems counterintuitive. But because of the characteristics of the slow, low reactivity and low flame speed of ammonia, it actually is well suited for that. Pardon me. So if direct combustion of ammonia, or other researchers are working on partially cracked ammonia, but the round-trip efficiency is higher if you can just directly combust the ammonia itself. And if that could be commercialized, that would be a long-duration energy storage pathway, and it could allow your combined cycles there to act as 24/7 dispatchable power. We've talked a little bit about, potential collaborations in the future on that, and I'd love to return to the island to do that. So this really may be an ideal clean fuel for those units, and I think working together that may be accomplished. And then finally, in the U.S., we're also researching synthetic aviation fuel production. One pathway under investigation for our carbon utilization division is to react CO2 from direct air capture, react it with clean hydrogen from electrolysis or other clean production means to produce synthetic aviation fuel. I visited a plant in Brooklyn, New York last year. They've successfully demonstrated the concept using bottled CO2. There's no direct air capture hub there yet, obviously. With clean hydrogen, and they produce SAF. Interestingly enough, they can also produce vodka. And when I was there in October, I asked to see a sample of their synthetic aviation fuel, and they said, well, they've been so busy making carbon-free vodka for the non-governmental agencies, the environmental agencies in Washington, D.C. to serve at their Christmas parties that they didn't have any synthetic aviation fuel to share with me. But SAF really could be a fuel also used here on Gran Canaria. It would be a suitable fuel. Obviously it's designed for aviation, but it would also be a suitable fuel for those combined cycle gas turbines. So another potential crossover there. And then I was surprised today when I learned from Celio Buendia's presentation that you're planning to also do biomass and waste gasification, another area that my division works on. And so that's a key pathway to net zero hydrogen, and that's really one that our group is really, really focused on, making that pathway economical so that we could have truly net zero hydrogen produced under that pathway. So I guess in summary, the BIOGREENFINERY is an exciting project. It's demonstrating many of the same pathways that we're demonstrating to decarbonize fuel and products here on Gran Canaria. And so I can put your researchers in contact with relevant research teams on the U.S. working on bio-based fuels and products. I already connected someone with the Ammonia Combustion Working Group, which is another group that we've organized for our combustion turbines colleagues. We meet monthly. Researchers and companies share work that they're doing and some high-level result on high-level problems perhaps that they're running to. And as we're all stating, and it's becoming more and more obvious, these types of collaborations are really going to be essential to accelerate the decarbonization and drive the world to a net zero future. Thanks so much for your attention. A big muchas gracias to Salvador and Santiago for our tour of the refinery yesterday. It was very informative, and I'm sure you all enjoyed that tour as well today. And thanks very much.
Robert, thank you for being with us. It's been a real pleasure having you here and celebrating your next holiday, birthday again in Gran Canaria. So you should get used to it, okay? So yeah, it was a very interesting perspective of all the H2 roadmap of the US. Aiming at 52% reduction by 2030, but going to net zero by 2050.
Yes.
So that's a very ambitious goal.
I agree.
Department of Energy, I guess, has the backing of all the U.S. government in this idea of progressing towards that very ambitious goal. He told us about how well it's working, the public-private partnership with this leverage of 6. That is managing to mobilize a huge amount of, I think you mentioned $50 billion dollars mobilizing for this transition. And
that's just for the hydrogen hubs,
that's
by
for
the way.
just for hydrogen, right. Yeah, you were talking about 10 million tons of hydrogen, maybe 3 in the short term.
That's right.
Yeah.
That's right.
And then, well, the resilience of the electrical system, what he has been able to see, at least in Gran Canaria, and it's not only batteries, also the different pathways of hydrogen, and how, going to even SAF, not only for air transport, but also for backing up PV and wind in these scenarios of growing renewable energy penetration in the island. So thank you very much, Robert. Very interesting perspective. We appreciate it. Yeah, and now our last presentation. Okay, yeah, from Airbus. From Airbus, we have Francisco Escobar, Architecture and Integration of Airbus Operation. Francisco, the title of the presentation, as I have it here, because Francisco, he confirmed yesterday, no, was it yesterday?
Just the day before.
The day before, yeah. The agenda, Francisco, is very complicated, so he managed to make it to Gran Canaria and to be with us, and we really appreciate the effort, Francisco. Okay, so he will be addressing decarbonization of the air transport sector. The floor is yours, Francisco.
Thank you very much. I think was that the one working USB. Is that one? Okay, thank you. Sorry, because I had some problems also with the way to share the information. I will manage to make you available a copy. Coming there? Ooh.
Is this the presentation?
No. Is that okay? Got it. The cable. Well, it's good enough. Okay. Good afternoon, and thank you very much for the invitation. Sorry for Susana was the first invitee, but she didn't manage on the agenda. It was a very tight decision to manage. We're working together. She's my boss actually on our organization, and maybe to develop a little bit further. We are working. I'm responsible of the airframe architecture and integration in Airbus operations in Spain, in the Spain perimeter. Airbus operation meaning the civil division of Airbus, and we will brief here you some our view of the challenges that the decarbonization, the sustainable aviation fuels, whatever other applications, like the hydrogen, the famous hydrogen. This is the main core of the discussion here. What are our challenges? What are our visions on applying that in our business? Okay. Well, starting for the basic ambitions on our view in the mid long-term future. As already commented, there are some links here with the last presentation, also with Paul on the R&T and R&D approach. I will comment, and also with Eduardo when speaking about the storage. Think about we are going to see here our view on the aircraft. I mean, we are kind of end users of most of the things we have been seeing in today here. Okay, we are trying to design those beautiful birds to fly around. For you to have figures, I was recapping this morning. According to the air transport, the various air transport provision sources, we are speaking about that in the next 20 years, the air traffic, basic air traffic, this kind of airplane growth is in the order of 40,000 airplanes needed, split basically in two-thirds is a brand new aircraft coming along, and the other one-third is more kind of replacement. But the two-thirds of those 40,000 airplanes is new ones that should come with new technologies, new performance, etc., etc. So part of it is one of our targets is already commented SAF. In our, you will see later, in our Airbus world, we translate to sustainable aviation fuel, synthetic aviation fuel. There is various sources, but we as end user, we want to receive the fuel and we want to demonstrate what's happening. I hope my connection is not lost, because I'm connected through that stuff. Okay, sorry about that. And our ambition, as of today, we are already flying, and we are qualify and certify our products to fly with regularly with 10% up to 15% in our internal fleets, meaning our flight test prototype, the Belugas. I don't know, you're familiar with the A330 Beluga, this big white airplane flying across Europe, transporting our parts. They are flying also with SAF already. And in some special cases, we have been qualifying up to 100% usage of SAF in one engine of the aircraft. But our target, as said there, is to reach full qualification of our complete product fleets by 2030. Okay? That means, we were chatting before, that means we are qualifying our products. The problem now for us is the availability, all the network and all the stuff we have been speaking about this morning, okay? Part of that ambition is to develop, we are on it now, develop a commercial airplane flying with zero emission, net zero emission aircraft by 2035. I will develop that later a little bit, okay? Reaching the net zero CO2 emission by 2050, according to the ATAC. The ATAC stands for the Air Transport Action Group. It's a kind of non-profit group of interest made out of the engine manufacturer, aircraft manufacturer, airlines, air transport, services, etc., etc. More specific details of this kind of airplane. We are targeting these development activities in this, I will call it two big families, and I will explain more on the flying wing, on the blended wing body. Our first target, actually the entering into service, sorry, this EIS stands for entering into service 2035, is for the first one. We're speaking about a turboprop, up to 100 packs, similar to the one, the ATR you see in the airport. I saw in the airport upon landing this morning, and around 1,000 nautical miles range, okay? The figure you see there is a baseline aircraft configuration, but we are, part of the study is that we will stay with a 2 turboprop engine, maybe 4, depending on the arrangements and depending on the system architecture, the hydrogen system architecture, okay? The other two on the bottom are two turbofan, larger one, more like on the scale of a normal A320, Airbus A320 you see across, coming and going every day from Iberia, in two major configurations, the commented blended wing and the classical turbofan, the classical tube and wing architecture, okay? To work on that studies are not just because of the revisiting the efficiency of the blended wing body, is because the chains of implementing hydrogen are so challenging, are so large. We are speaking about new system architecture, new system of storage, new way to certify. I will come later on that everything is new. So here, the blended wing body study is also coming across to the advantage and drawbacks of this aircraft architecture, but also analyzing the implications it could have in the hydrogen new approach. As I repeat, everything hydrogen has been very well explained over the complete morning. I will not spend more time on that. It's obvious the energy density by mass is there. Our problem is the volume, as you will see later. And this is why those architecture are there. The number came there. Our numbers is the 3 times in mass energy versus standard kerosene today is clear. Depending on the application of the hydrogen, whether high pressure gas up to 700 bars, that was the reference on the studies. We are exploring even higher pressure for certain gas hydrogen application in the aircraft, or the cryogenic liquid hydrogen, we are speaking about in between 4 to 6 times the volume of the fuel. Remember, on the today aircraft, the fuel is going on the wing, the wing box. The main wing box structure is the tank, and it doesn't work for a pressurized liquid. Okay. Well, our expectations of the market. This is more on the rest of the presenter. It's assumed the supply chain, etc., will change the model of the cost and also the versatility of that magic fuel. The main challenge on us, speaking on very specific things, very simplified. What I said is storage is the key. You need to storage in kind of quasi-spherical, because of the pressure, quasi-spherical. Even for aircraft efficiency, the cryogenic liquid hydrogen should be pressurized, because if not, it will be even higher volume. But we are speaking about big tanks that need to be set in somewhere there. On the basic tube and wing configuration, our reference is to make so-called caudal tanks on the rear part of the fuselage, but also we are exploring other alternatives. As said, the regulations. We are here, we are doing really a major jump in how the approach should be to develop, to certify, and to operate this future aircraft. And we are working together. There are not today regulations. For us, it's a much higher jump that when we have been confronting other new regulation linked to the very early primary structure CFRP composite parts on the airplane or the fly-by-wire. Was a kind of a step, and we were working with the regulators, and we certified today in the near future for the hydrogen. There are so many changes that even the regulation is a big challenge. We are working together with the EASA, we are working together with the local, we are collaborating with our INTA colleagues in certain research projects and development projects on it, okay? The infrastructure, part of the things deeply discussed this morning. At the end of the day, we are the end user, but Airbus, in part of those working group and other, we are promoting the networking on all the infrastructure, logistics, etc., around that, around the airport, around the airplane. Well, again, the assumption on the H2 availability, the hydrogen availability are costs. At the end of the day, has been well described in the latest presentation. Our expectation and our way to attack that is assuming that eventually we will need to understand what will be the basic economy of the aircraft in a more already established ecosystem, I would call it. Prior to those aircraft, the ones you see are what we call product development, but we are in the middle of preparing this demonstrator. We are taking one of our A380 flight test aircraft in Toulouse, and we are converting it, putting an extra engine. The aircraft, the A380 is so big that you can see the engine, but there is a turboprop engine there, and also here. We are doing a plug-in in the rear fuselage of a test. Basically, we are combining here, we want to test all the possible arrangements, not only on the propulsion, but on the storage and the distributions. We are trying to test H2 burn, H2 combustion engines, directly applying to in a simplified way for the engine guys, is to redesign the combustion chamber to put the hydrogen up there. There is more things later, but this is the basic. And the other one is the well-known using fuel cell to convert the hydrogen on electricity, and then the electrical engine. And part of that was a subscale demonstrator that was already shown on last year. The target to fly that A380 is around mid-2026, depending on how it is evolving. And that will set basic understanding of the technologies, of the challenges, etc., to feedback those developments. Okay. One particular issue are the tanks. Eduardo already explained, and I wanted to show here that specifically inside Airbus, as a kind of priority out of the overall hydrogen system and distribution, we are very focused on the tanks. Cryogenic tanks is a state of the art, has been well explained for the launchers, rocket, but this is a kind of one-go issue. We are thinking, we are trying to understand what is the best tank arrangement and the direct system for a normal operating aircraft. We are speaking about 25 to 30 design service goal operating an aircraft. And again, volume and time is a major driver here. So we are internally in Airbus, we are exploring the optimum storage system in terms of material and arrangements. Thank you. Well, conclusions. It's a great challenge to get that. Here I want to remark in one figure that is on the media since year already. Their traffic is contributing around, depending on the sources, we are speaking about 2.5% to 4% of the overall CO2 emission. Being small, we need to do our part of the cake, but the challenge we face on the aviation are huge. As I tried to explain, reducing that tiny things on these particular airplanes is very, very, very challenging. It's challenging everywhere, but it's much more challenging than in a ship going around there or in the beautiful buses driving around Tokyo. You know, so the challenge is huge. The challenge is huge. Actually, what we believe is an exploration of understanding the scalability of an hydrogen system, or at least a direct application of hydrogen as fuel, because there should be a limit. There should be a limit. Out of that limit, we need to jump to this kind of whatever version of the sustainable aviation fuel, SAF. A big airplane crossing a double aisle wide body, crossing across the Pacific or crossing across the Atlantic for 6,000 nautical miles doesn't work. That's the same point. We want to lead. We are actually leading that development at that scale, and we need to understand the journey of using that sustainable aviation fuel, as I tried to explain. And the last point is that also this is one of the, we as airframer manufacturer, is one of the core of the research and development we are investing on. It's not only aircraft architecture, it's not only system architecture, it's new materials in the widest meaning of the new material technology. And I think that's all. Thank you very much.
Thank you very much, Francisco Escobar from Airbus. We appreciate very much the effort to be here with us. Well, Francisco, you said that the industry is headed toward net zero air transport by 2040. He said that about 40,000 new aircrafts with new technology should go into the market in the next years. Airbus is aiming also 2030 to have a 100% SAF aircraft. I'm not sure if when you talked about the A380 flight in 2026, would that flight be 100% SAF? No.
It's in one of the options. Sorry, maybe I didn't explain properly. The first version to fly will be maybe a hybrid or hybrid gas to liquid engine feeding a fuel cell. But part of the development to be flying on the same demonstrator will be also a SAF.
Ah, okay. Okay.
But the SAF I explained are the one using on the main propulsion engines.
Okay.
Okay. Maybe I was
Yeah,
not
yeah.
explained
You
properly.
mentioned that in the 380 you would have 2 engines on the fuselage in the rear part.
That additional engine,
Yes.
that fifth engine,
The fifth, sorry.
is going to fly on hydrogen. The first flight is on hydrogen basis.
Only
in
hydrogen.
hydrogen. Yeah.
Okay. And well, yeah, you made it clear the Airbus is a final off-taker. You are not into the business of producing the fuel. You only do the technology to make it possible for a plane to fly with those clean green fuels. And well, you also said that probably all the certification procedures currently would have to be a lot of them revised to the new technology changes.
It's really brand new. I repeat, we are working together. The certification bodies are working with us. We are working with the EASA, with the FAA in United States to understand the new regulation. It's the string case I know in my experience that we are developing the core of the new certification in parallel to the product. The regulation are running in parallel to we are developing the aircraft.
Okay.
So it's really challenging.
Yeah. Thank you, Francisco. A pleasure having you with us here. So the second session has just finished. So if you have questions for not only for Francisco, for any of the speakers, I guess the microphone. Okay. So please feel free to ask any questions you would like to make to any of our today's speakers.
Is this working? Yeah. I thought I'd kick off with I'm retired, so I can ask silly questions. Why is Boeing so gutless relative to Airbus? Sorry, you don't have to answer that.
Not truly. We don't know. We don't know what. Either what are they doing in terms of sorry.
Yeah, because Francisco, we have people on streaming, so it's.
Yeah. Sorry about that. Here there is a, in my view, that's Paco's view. Okay, is as you, we are not highlighting the more specific details in certain technologies, in certain strategies, obviously, but you can understand, but neither the AI. But the game here is very tactical, I will say. So and now it's very linked to the main difference, in my view, in between Boeing and us is that how is their view now in the current product and how they will position, how do they move, they do the strategic move on the next few years to understand if their target is in terms of aircraft configuration, in terms of aircraft range, and in terms of technologies, will be very much depending on when you move the first piece. You know what I mean? Beside that, on specific technologies, we are somehow blind. Yeah. Okay.
Thank you, Francisco. Any other questions? If not, okay. Yeah. Bless you. And if you can identify yourself when you make.
Yeah, Ramon Castella from Carburos Metálicos Air Products Group. Just a question for Eduardo. I'm not sure where it. Okay, it's about you were talking about storage. Okay, we are producing hydrogen as well, but talking about underground storage or under the sea or under something. This is a reality. Some tests are done, or which is the situation today? I'm thinking in the natural gas trials done in Spain, where it causes earthquakes and something like that.
Well, thank you for the question. Yes, the storage of hydrogen in underground geological formation is a reality at small scale and pilot scale. So there is, not now, even from, if I remember, in Louisiana, in the USA, also in the UK. So there is some applications, okay? Hydrogen, also mixture of hydrogen with other gases. So there is an experience. Yeah, and this is why we can say, okay, what is the maximum pressure? What is the maximum volume, depending on the formation? What is the typical losses we have in this kind of storage? Okay, but of course, there is a lot of work to do that can be used in a reality for large scale. Not only offshore and onshore, but is in fact there is some European projects in this way to test. I think the last call that Pedro has presented, there is some topic about underground storage. Okay.
Thank you, Eduardo, for clarification. Any other questions for the speakers? If not, I'll make one. Well, to pay. Okay, sorry, John. Yeah.
Thank you. My name's John Chamberlain from Naturgy, and I've got a question more to the international colleagues here. The first thing to the American colleague, you've talked clean hydrogen. I'm guessing in the short term you're talking blue hydrogen, which is a complete different strategy to Europe, especially Spain, where it's green or nothing. So I'd like to know what your views on the technology development is. And the other question, just to the general other two things. We sit here, we talk about the huge hydrogen challenge, but it's the biggest challenge we face because the conversion to get there is huge. From your own opinions, where do you think the real hard part is? Is it in the production, the transport, the storage, or the usage? I'll leave it at that.
So it's easy to just pass the mic. That's kind of nice. So U.S. has such diversity of resources that, yes, we do see blue hydrogen, or we call it clean. We try not to use colors in fact, maybe even by 2050, there still will be some of it used. Some IEA projections say that very thing, that carbon capture and storage will be still important that far into the future. Our definition of clean hydrogen, like the Inflation Reduction Act's tax credits, define the top end as 4 kilograms CO2 equivalent per kilogram hydrogen. But this is based on a rigorous life cycle analysis that includes upstream emissions, so if you're using natural gas, any methane emitted at the production site or through the transportation pipeline system is counted in that total. And then also the electricity grid feeding electrolysis would also be counted in that total as well. So we want all sources of hydrogen to compete on an equal greenhouse gas basis, and that's why really life cycle analysis, very rigorous life cycle analysis is an important part of that. Our National Energy Technology Laboratory, I think, is one of the world leaders, if not the world leader, in life cycle analysis. They have multiple papers on the subject. They do a really comprehensive Scope 1, Scope 2, Scope 3 emissions, even they'll look at in the manufacturing process of the components assembled into the hydrogen production facilities. So I hope that answers your question.
Yeah, I think Robert, the other Robert also wanted to comment on John's.
Yeah, I was going to comment on the second part, but I'd like to comment on the first part as well, based on Rob's answer. For me, the crux is certification, whether it's blue or green or other colors. The whole blue-green thing is out the window now. It's about how much, if I got a kilogram of hydrogen in my right hand, how much of that is inherited CO2 emissions. So, anyways, there's one of the tasks, what is it, task 47, I think, of TCP is focused on integrating all of those certification tasks around the world. So, yeah, watch this space. The I can't remember exactly what your second question was, but another way to put it, rather than the hard part, where's the sweet spot in terms of investment in solving the hard parts? And for me, that's scalability, big time. Because, for example, I know Australia best. Our largest electrolyzer right now is 1.25 megawatts, and yet there's many projects, like I can't remember, 10 or so projects, well beyond 20 gigawatts in scale. So how do we go from these little toys to vast systems? And there's a lot of questions to be answered in that regard, but yeah. It's, I guess I'm biased in that I'm part of a request for funding from the Australian federal government to look at scalability.
Thank
Anybody else have a
you. Thank you,
comment
Rob.
on that?
Thank you, and thank you for your question as well. From the side of the European Commission, what we see is that first, this conversation about the egg and chicken suppose dilemma. We need plus hydrogen, but we need the demand for it. What comes first? Both come first. So we need demand and supply at the same time. We need both, and we cannot wait for one to start. Otherwise, we will start too late. And we need that solution for today, right? But in general, which field were we seeing right now as the weakest link, or what we should be investing more is, as I mentioned in the presentation, is storage. We believe that storage right now is really not enough at all in Europe to satisfy our demands of producing and of importing, and we want to make sure that we are self-sufficient. So I would say, I don't know if the member states would agree, but storage right now is the most important for us. Well, the idea of the European Commission is that imports will be just on this transitory phase. The idea is that we can produce hydrogen on our own in European territory. That's why we are funding mostly hydrogen production technologies in the Clean Hydrogen Partnership, because we want to make sure we produce our own hydrogen and don't rely on imports. Imports can help, of course, and we live on the global market, but the idea is that it won't be a final solution. It will be just for now.
And to go back to your question about use, a really important part of the Hydrogen Hub applications where we required off-takers to be included in the hub application. And so, for instance, the California hub is pretty much focused on medium-duty, light-duty transportation uses of hydrogen, which are somewhat more developed than a lot of the industrial ones. But the Gulf Coast is really focused on decarbonization of refinery and petrochemical production. The Midwest one is really focused on producing decarbonized ammonia for fertilizer. We have the Appalachian Hub actually has several off-takers. There's a steel plant that will be a first-of-a-kind demo in the U.S. There's a cement plant that will be first-of-a-kind. There's a large power generation station, a natural gas combined cycle unit that will take hydrogen from that eventually. And so that's, we tried to build in demand to our hub so that all of the different industries would get, first-of-a-kind demonstrators of how they could decarbonize their operations with hydrogen. And then the market's going to decide as, we drive the cost of hydrogen down and increase the supply of it. There, hopefully more people, as it becomes more and more competitive with the dirty fuels, more and more people will adopt.
Yeah, well, I have a question myself for all of you, especially Robert, Pedro from the European Commission, and even Santiago from IDAE. I don't know if he left. He left, okay. Yeah, but maybe the European Commission, also the Department of Energy. I mean, we're facing here in the Canary Islands at least a dilemma a paradox, of a vicious circle, where you don't have hydrogen production because there's no demand for hydrogen. There's no demand for hydrogen because you don't have hydrogen production. So when addressing the issue, you should look at the whole value chain. I mean, you have to go together. You have to invest in electrolyzer, but in buses and cars. Not just cars and buses and forget about or just electrolyzers, because then who is going to buy you? So, I mean, I don't know, Department of Energy and the European Commission, how are you really aware of the need of going in the whole value chain together? Not because, I mean, for Valley, H2 Valley, the last call, we submitted a proposal. And yes, it seems after that the score we got was relatively low, but I think that the European Commission was not really looking for what we proposed, that was working on transport and hydrogen production, demand and supply together. It seems that probably you were looking more for substituting gray hydrogen with green hydrogen. I mean, looking for projects where demand already existed for hydrogen, not green hydrogen, obviously, but for the one obtained from natural gas. And what you wanted was somehow just that people invested in the electrolyzers to substitute the demand from an established industry, not for a demand that doesn't exist. That's the sense, the feeling I got from reading the evaluation report. And I don't know in the US if you are approaching it that way. I mean, in the whole value chain together, investing in electrolyzers and the demand together, not just creating demand on a place where there's no hydrogen, or investing in electrolyzers in a place where you know that there's no demand. No? Yeah.
No, it's on. Okay. So besides the dedicated off-takers that are parts of the hydrogen hubs, Congress gave us $8 billion to award for hydrogen hubs. We only used $7 billion. The last $1 billion we're holding in reserve, and we're going to be issuing funding opportunity announcements sometime in the medium-term future to develop demand drivers for that hydrogen. So right now, it's all carrots for production. We have the production tax credits. We have the CO2 storage tax credits. So we have a lot of carrots for the production side, and we're all working, all the different offices, renewable energy, nuclear energy, fossil energy, and carbon management, we're all working together to develop what that last $1 billion worth of demand drivers is going to look at. And it's a difficult question. That's why we want to get the hubs under construction and partway along the way before we issue that, and so that we can grow the demand around those hubs.
Thank you, Salvador. In fact, I would say you got the concept right. That's precisely what we want. The idea of Hydrogen Valley. I don't know if it is clear on the call. I don't have the text in my mind right now, but I think we specified there that we want, in particular, Hydrogen Valleys to be used for one or two different end uses, and mobility is one of the end uses that the joint undertaking has funded more projects. So we want indeed to replace the production of gray hydrogen with green hydrogen. So we want to fund out of electrolyzers, but the concept of the valley itself is precisely to tackle this problem of what comes first, demand or supply. We want with the hydrogen valley to create both at the same time. Well, I don't know if it's the correct expression to say, but we want that when a developer has the idea of hydrogen valley, they already have the idea of the off-takers and of the production, which is precisely what you want to do here. And here in the BIOGREENFINERY project, you have both the electrolyzer and both the bus for the end use. I would just advise to apply for next year.
Okay, thank you, Pedro. We will. Eventually, you always get it approved after a third or fourth. Yes. Any more questions? So, well, the session is finished, and for today, the conference stops here. Tomorrow, we will be back at 9 in the morning, right? Okay, and thank you all for coming, and the colleagues on streaming, thank you for, and again, we apologize for having you waiting for the session, okay? Thank you, bye.